Good morning. So I think now that we are three of you are there, I will start. So this is a bit of a shame that there are so few are joining, because if you want to understand the rest of the course, this is the most important day. But we'll see how it goes, and we have the video recording, and I will publish the slides as well. So this is the book, as you saw this morning, that the book you saw yesterday. New edition. I just received this morning the last version, I think, of the proof. So I made last few corrections, and so but it will be now printed, second edition. So now currently we are in the third wave of AI. So we have AI has been a big topic in the second half of the 20th century, and now we are in the third wave of AI. So what does this mean? So we had since the 1950s, when the term AI was coined, we had three big AI waves. The first one was about logic systems and simple stochastic models. So the logic systems, here you see an example of one made by pioneer Weizenbaum, Joseph Weizenbaum. This is the first chatbot, Eliza. It was supposed to mimic a psychotherapy session. Of course, it didn't really work, but it was kind of a deterministic attempt at AI. When you play modern computer games, still a lot of the dialogues are like this, right? So if you interact with NPCs, so I mean, I haven't been playing computer games, unfortunately, in the last 25 years, because I had no time, but my children do. Sometimes I see what they do, and the chatbots are still very often built deterministically, which is also why NPC has become a negative term for real humans, for people who are stereotypical in their reactions and seem not to reflect very much what's going on. They are now called by my children NPCs, and I think that is the reason these chatbots. Now, what there also was in the 50s and 60s and 70s was quite a lot of stochastic AI. And we will learn quite a bit about what that is today. But stochastic AI is basically an alternative to deterministic AI. And then we had in the 1980s and 1990s, the second wave of AI was around so-called expert systems. So they were used quite a bit to basically make knowledge available in an interactive form, so that you have and the most important one was IBM's Deep Blue machine, which won against Kasparov at chess in 1996. I remember this. At the time I was 26 or 25. It was quite shocking, and it was also the first time that I tried to understand how this works, and we'll come back to this in a bit. Then there was kind of a crisis of AI after that. There was a crisis of AI after that because the AI systems did not have any economic impact, right? So there was basically technology that has no economic impact is seen as failed, right? So in the 1970s, there were two video recording systems, Betamax and VHS. And VHS was a worse system, but it made it because it was much cheaper, though it had poor quality, but the consumer market was completely dominated by VHS. And so Betamax never had gained any importance. That's always the case when technologies fail to get economic impact, then they basically lose any importance. That's what happened to AI. There were a lot of newspaper articles and books mocking AI. It was a silly idea. And then in 2012, Google created the first neural network that was able to do a very impressive clustering on images. And they basically they clustered using this algorithm images of animals. And in one of the layers of the neural network, they could see a simplified, abstracted, representation of of the face of a cat. So they claimed in 2012, and you may remember this, although this is also now 13 years ago, that Google had thought and created an abstraction of a cat-like human being. This is not true that it thought, but it was very impressive. And very soon thereafter, they published a classification algorithm which was able to classify very accurately the type of animal visible in a video. And so this was a big breakthrough. And then 2013 came Google Translate. And Google Translate and the neural machine translation revolutionized translation, because before that, machine translation never worked at all. And with Google Translate, suddenly it worked pretty well. So it achieves a good approximate translation. Now, if you know Japanese or Chinese, which I don't know, but if you know this and take a Chinese web page and put it into Google Translate, for example, Wikipedia article, you see a lot of mistakes, even more than if you try French to English, French to German. But if you take a text by Hegel, for example, one of the most difficult texts that was written in, or a paper by Einstein, put this into Google Translate, you also find a lot of mistakes. So it is not an accurate translation, but it is a translation that is very helpful to get a first impression of what this is about. If you want a precise understanding of what it is about, you need more than this. But the new machine translation was quite something, and convinced a lot of people, including myself, that now this AI winter since the late 90s was over. And then came AlphaGo and ChatGPT, which of course made even more fuss. Though one has to say that in terms of productivity increment, the machine translation is the most important impact of this new AI wave that we have had so far. Now, this has now driven such a hype that when I had my own company from 2014 to 2024, and during that time, many customers, and it was an AI company, and I founded it because I wanted to participate in this hype economically, and it worked quite well for a while, but not in the long term for complicated reasons. But when it worked really well, I could not even keep up with all the demand. Customers asked me why I don't do chatbots. And then I explained it to them, and they keep on pounding, no, that can't be. It must be possible to make chatbots that work. And I said, it will never be possible. And then I got fed up and wrote this book to really give the real reason why it doesn't work, together with Barry. So now, at the moment, there's a real AI hysteria. So even scientists are confusing reality and sales language. So AI is a sales language, right? So artificial intelligence is a term that was invented to drive the sales or to get funding for AI. And if you look at OpenAI, for example, this is a company which has now obtained something like 30 or 40 billion dollar funding. Though the company has just, I don't know how many employees they have, not a couple of hundred or so. They are a small company, but they have obtained more funding in their short history from the state than probably Siemens, the maker of huge plants and so on. So and with funding, I mean really startup funding, and so why is this possible? So Elon Musk in November 2023, he said that soon we won't have to work anymore. The machines will do everything. And it's absolute nonsense. He also says that there's a danger of machine domination, that machines will take over the world and rule us and so on. Therefore, we need a lot of regulation. Now, I don't know whether Musk really believes this himself, or whether he indeed uses this to protect his own investment into AI. Because if you are, if you claim that something is very dangerous, where you have a strong position as a market participant, you may also do this to prevent others from entering the market. You see this a lot in banking. Banking is extremely regulated, because if you have a bank, you can create money out of nothing, give it to people and ask them to pay interest rate on it. So you have actually created the money out of nothing. And so this is a great way of making money. And if everybody was allowed to have a bank, the system would break down. So therefore, those who have banks, when they created the central banks, they also created a regulation that makes it extremely hard to become a banker, an independent banker. And so this is basically the same here. So there may be an element of trying to raise the barriers of market entry for other participants. Geoffrey Hinton just received the Nobel Prize in, I think, physics for a version of stochastic AI that has never had a lot of influence, and that was not of central interest, unlike Schmidhuber, who teaches here as well, who is, I think, a genius in AI and who deserves the Nobel Prize. Hinton has not deserved it. I think he received it because of his political views, and probably because he's also more sellable than Schmidhuber. He believes, so he was a former head of the Google Brain department. He believes that AI can soon surpass the information capacity of the human brain. He believes that now already machines are conscious, that chatbots will have the ability to learn independently and to form a collective, like humans can form collectives, that AI will overpower human beings, and wipe out, I could wipe out humanity, that general intelligent AI system could create their own goals that do not coincide with the interests of us, their programmers, that AI systems would become power hungry, prevent us from being them from being switched off by us. And so all of this is absolutely pure nonsense. And the only aspect where Hinton is right is that AI systems used as weapons are really dangerous and require regulation. So this is indeed true, and we will get back to this aspect in a bit. So now we heard already yesterday something about intelligence. I want to systematize this a little bit. So we have to analyze this claim, whether there can be AI or not, we have to first of all understand what AI is, what intelligence is. So animal intelligence is a form of intelligence that is realized in humans and some higher animals. It's the ability to adapt to new situations with the following properties. The adaptation is sudden and is not something that is primed by prior experience. It is meaningful, which means that it is appropriate to the situation. It's untrained. So it's not a product of repeated attempts at trial and error, but yes, just a second, it happens immediately, and it is novel from the perspective of the acting organism. Yes, please, question? I think that Hinton is a psychologist. Hinton is not a mathematician. And Hinton, I think Hinton's understanding of how AI systems really work is, probably he does, but I don't know. It's very hard to tell why he says this. So I think on the one hand, he is only dealing with people who are completely in this AI euphoria, right? One of the reasons why my company failed is that I was telling the customers what AI can really do. And they wanted to prefer to go to charlatans and buy some snake oil. You know, they didn't want to. And now, of course, I see that this has led to crisis. So the pharmaceutical industry, in which I am now working again, they have spent billions on AI on these promises. So they really thought, so McKinsey consultants were telling them that in 3 years, this was 2 years ago, AI would lead to a factor 10 reduction of the development types for drugs. And they were pointing at the mRNA-based vaccines and saying, look, they were so fast, and this was all due to AI, which is complete nonsense. And so they were claiming, making these claims. Then the pharma industry invested millions and billions, and they failed. Nothing changed. The speed didn't increase. And you will learn why. So there is a lot of real heat and excitement in this whole industry. And I think Hinton is just within it, and he's only talking to people who are like this. And there are many, many people we cite in our book, and we have updated this section, who are real insiders and who do like I do, the development of AI systems themselves. I know personally, I don't know any of them who is also defending this hype. So most of those who really do the work themselves and are really getting into the details of how it works, they are totally skeptical. I think I don't understand why Hinton is like this. Maybe also that he received the Nobel Prize has narcissistically manipulated him, or I mean, it must be quite something to get the Nobel Prize. I never get it, so, but it must influence you. I don't know what's going on. I'm also not a psychologist, but we will see why these claims are actually plainly wrong. I mean, this is just an announcement to get you a bit interested in what is coming now. You will see why I think it's fundamentally wrong. And with a lot of engineers who don't understand the mathematics of AI systems, I think that I understand why they believe it can be like this. Because they have, on the one hand, they don't understand the mathematics of the AI systems because they're just users. You know, like engineers are very often, you know, sometimes when I teach and I go to the classroom and there's before me an engineering lecture, I'm always astonished how these engineering lectures are. So basically the professor shows to the students a text with requirements, for example, to build a bridge or an airplane. And then the requirements are listed, and then he has colored some of the words in different colors in the text, and then he shows an equation. Now the engineer has to pick in the catalog of equations the right equation, and then he has to instantiate the variables by looking at the text. So the engineer translates the text into variables for the equation, and then he puts the right variables in to calculate properties of the system that he's going to build. And so this is how engineers operate. I'm not saying this is not an art, but of course they have not created the equations. right? So they have, the equations were created by mathematicians and physicists, and the engineers are users of the equation. Very often they don't reflect them at all. And I'm not saying this to criticize engineers. Without engineers, the whole modern world in which we live would stop and grind to a halt. But they are applied scientists. And in this way, computer scientists are also applied scientists, and many of them don't reflect the mathematics. For them, actually, having to pass mathematics exams on their way to become engineers, they curse it. They don't want this. They just want to be engineers, right? And I'm not even criticizing them. That's I love mathematics, but it's not everyone's taste, And so I think that's also, on the one hand, they lack the mathematical insight into the nature of the models. On the other hand, they lack insight into the nature of the human mind. So they believe the human mind is a very big pocket calculator, right? Like this here is also a big pocket calculator because it can do more. My first pocket calculator was of this size, and it could, I think, it was a Texas Instruments programmable. You could program it in Fortran. It was built in 1980. It was a bit heavier than this iPhone, but it could only take, I think, 30 lines of code and execute calculations up to, I don't know, 2 to the power of 16, and then the stack was full. And and they just believe that the human mind is just like, this is more powerful than the pocket calculator of the 1980s was. They believe the human mind is just more powerful than this calculator. And so I disagree with this view of the human mind, as we will see a bit later. So now going back to the definition of intelligence, these are the properties, and the most important one is that it's untrained. And this is really fascinating. When you drive in a car, as I do with my children when they pass a driver's license and they get to drive me around, right, which is normal. We switch driver role when we are driving long distances. And then they get into situations they've never encountered before, in which they would be involved in an accident if they would take the wrong decision. But they haven't learned this in the training. They just learn how to drive the car and the basic rules, but then they react in an adequate way. Though it's a new situation for them, and this is the sign of human intelligence, or actually animal intelligence, that the capability of finding the right situation is untrained. And none of this, all the software that we have today that is called AI, fulfills nothing of this. It's heavily trained and configured very massively to fulfill a certain task. So it's not sudden, it's not untrained, it's not novel, and it's also not meaningful for the machine. It's only meaningful for us. That's also important. Because the machine only does symbolic operations in an electric circuitry. Mental intelligence, which is stronger than animal intelligence, has another few sets of properties. So it's temporarily independent from the immediate organic necessities. So that means that you can basically suppress the necessity to breathe, to drink, to sleep, to eat, for reproduction, right? So all of this you can postpone. Monks even postpone the necessity for reproduction for their entire life, right? And so and animals cannot do this. Also, so if an animal has the opportunity to have sex, it will just have it immediately, right? So the animal will not wait for privacy or for the night to fall or anything, it will just do it. The same with eating and so on. Humans can see central inputs as a matter of objects. So that means that we can abstract. So I can abstract from this, right, object and make it belong to a class, the class of envelopes or protective, I don't know, leather tools or whatever. I can classify it, or I can classify this as a type of computer, and this is another type of computer, and so on. Animals cannot do this. So there are many experiments which show that animals can only see the concrete instance of the object, not the object. Also, humans have self-distance and distance from the environment, and self-consciousness, so they can see the world as an object, which Max Scheler called Weltoffenheit. So it's an openness towards the world, which rests on these properties. And this openness towards the world lets us engineer totally new things that have not been there before, because we can imagine the world in a way that is different from which it is today. Animals cannot do this. Animals can only interact with the world as it is. But I can have a problem and now look at my environment and say, what in my environment can I use and modify to solve the problem? And this is a fundamental property of humans. Also, humans have personalities, which we perceive now. Of course, it's said that animals also have a personality, and I agree with this, that the dogs of the same race, even sibling dogs of one breeding, they can have different personalities, but they are not aware of their personalities and cannot express their personalities. So the singularity of which Geoffrey Hinton and Elon Musk are talking would require mental intelligence. So not only practical animal intelligence, but mental intelligence. And if they say, oh, you know, we need this or that, discussing the type of intelligence, it's crucial to be aware that basically we are talking here about mental intelligence they would require to do this singularity. Now, this is again the utility. Now, interestingly, the AGI community doesn't agree to this definition of intelligence, but they use a utility function, which is basically in the spirit of utilitarianism and invented by Bentham. And we have seen this equation yesterday. I don't want to because Barry has shown already, and we didn't really plan this, coordinate this too well. I will skip these slides, but just highlight some aspects. So basically, what Barry didn't show is that how the so this was the utility of an agent, but here's the intelligence, and this bit Barry didn't show. And the intelligence of the agent, which is an uppercase epsilon of the agent pi, is defined as the sum of the utilities it's creating in different environments. So you see here mu is an environment, and uppercase U is the set of all possible environments. And now there's a sum made about over the utilities that reside in every single situation. So now you have each instance of mu is one situation of the environment, and now the sum is calculated. And what is quite elegant in this equation is that the Kolmogorov complexity function K, which indicates the length of the shortest algorithm needed to computationally represent the environment description of mu for the agent pi. This is the complexity, and it's basically penalizing the utility. So if the complexity is very, very high of an algorithm, then the utility function is set to be lower. Though I criticized yesterday the infinity sign that is given here in the utility function, which is a bit abstract and nonsensical, using the Kolmogorov complexity function is very clever because it offsets long computations. So if you need a very long computation to get a utility, then you are penalized. And this is a clever way of, but you see this definition of intelligence yields, of course, the Hutter set of AI algorithms. And basically, it is basically the consensus of what proponents of machine intelligence believe is intelligence. And now you understand a bit, you who asked the question, why Hinton believes that you already have intelligence, because if we use this intelligence definition, then we have already achieved intelligence, right? So, good morning. So using this intelligence definition, you can say, okay, we have intelligence, but only if you use utilitaristic definition. Why is this definition inadequate? So the definition captures just one part of Schiller's definition of private intelligence. It lacks the three further constitutive properties of suddenness, untrainedness, and novelty. So it also the verbal definition of intelligence that they provide, that intelligence is the ability to adapt to novel situations. Here, intelligence measures an agent's ability to achieve goals in a wide range of environments, is too narrow because, according to this definition, extremely primitive organisms, even bacteria, are intelligent, right? But nobody would say bacteria are intelligent. So it's much too narrow, and so because bacteria can also perform this. Bacteria can basically create utility in a set of environments to which they are adapted. And they can get a good score. A bacterium or an amoeba can get a good score in this equation, but saying they're intelligent is certainly wrong. Okay, so now let's go through other problems of the definition. So this definition is very much focused on the environment mu, right? This here, because the utility function is defined using the environment mu, as you see here. And then, of course, the intelligence, which is the sum of all the environments, is also using the environment. And so therefore, we need to ask how the environments are captured, because in the end, this definition requires them to be expressed as a binary vector. And how can you do this? How can you express this? Well, what we have, of course, are sensors, right? So sensors enable machines to capture the environment using into a binary vector. And if you think of how intelligence is basically, how AI is used, most of it doesn't need sensors because it's deployed in the World Wide Web. And so if you are in a completely digital environment, you don't need you don't need sensors because the data are already there in digital form. But if you think of a robot freely moving, of course, in an open environment and not in a purely digital environment, then you need sensors. And why is this important? Consider an ego shooter game. Now, in an ego shooter game, computers have already been superior to humans since 2015, so since 10 years. And why this? Because all the information that are needed to optimize the behavior in an ego shooting game are digitally present. So the vectors are already given, and it's a closed world, and you can perfectly, using this definition of utility, you can perfectly train algorithms with so-called reinforcement learning to become arbitrarily perfect in this environment. And because that's the case, and you can show this mathematically, you can obtain perfect actors in this closed world environment of the ego shooter, which no human being can beat. And the only way to make this, to change this, is to make a game setting that becomes non-deterministic, because if humans can change the setting, for example, and work in teams and communicate by language. So if you have a team of players playing against an AI, and the team of players is allowed to speak to each other and to change the environment of the game by shifting around objects and so on, then it can beat the AI, because then patterns are created which are so irregular that the AI cannot cope with them. And we will get back to this. But if you have a closed world where the set U, the uppercase U set, is closed and predetermined, you can show mathematically that with reinforcement learning, you can arbitrarily optimize the behavior of the machine. And so therefore, what this shows you is that they have selected a definition for which they already have a solution. And that's a bit like I'm saying, I can fly. Look, I was just flying for 0.2 of a second. Yeah, but that's because I changed the definition of flying. And so now to perception. So if you imagine now the machine having to work in an open environment, the sensors are only capable of passive impressions. So what is a passive impression? A passive impression is, you imagine that you make a photo and cannot move your eyes, right? You can just make a photo and then you can react. Now, of course, you can have a camera that makes a photo and then adapts and follows the movement of an object, but it's very imperfect and it's still a passive impression. So basically, the concept of machines, impressions in the sense are electric signals of the same unprocessed form, but generated by sensors which have been engineered with a specific target type, span resolution. And this basically, so mammals don't perceive like this. Mammals have active perception, which is a mix of motoric activity and sensoric perception. And you have this, you can study this very well if you look at how a child learns to speak, because language is a motor function. When the child makes the first utterance, it also hears its utterances. And then it can correct its own utterances based on what it's hearing. You have a very, very, and it's the same as if you look how a child is learning to play. So when a child can sit at the age of 9 months, you can give the child the big Lego blocks, for example, or other objects to play with, and the child will start interacting with each object, and based on the interaction with the object, will refine its motor function. Of course, it also observes how you use these objects and imitate, but basically the child has a very, very tight circuit of action and reaction to refine what it's doing. And the machine doesn't have this. The machine has only passive perception. So the whole, what is put in this equation as environment mu is not at all the environment mu of a real intelligence. So perception is more than sensory stimulus. And I think the best accounts that you can get of this active perception topic is super important to understand. It's only one aspect of how humans work, but it's a super important aspect. And the best texts on this are Gehlen, who has in Man, this book, which we cite a lot in our book, describes this extensively in his chapters on language acquisition, but also Gibson. J.J. Gibson describes this very well for optical perception. And there are also contemporary studies like O'Regan and Noé and Howry, so more recent studies in this field. So it's very, very important to realize that perception is something active, and that we don't know how this active perception works, but we can observe it, and we cannot mimic it. So we have in machines only passive perception. The second problem of the dimension by Hutter is the motor activity. So I just said that the motor activity is an active loop with proprioception, outer sensation, and so on. And so the steps of the utility function described by Hutter, they are linear sequence of discrete actions, but human motor acts require fast and fine-tuned interaction of perception and motor activity. So which are also parallel and at multiple levels. But here, if you look at this, here you can only do one step after the other in a linear fashion. But in a human being, many systems work in parallel, right? So for example, when I walk now towards you while talking, I have a proprioception system that makes sure that I don't fall. Yeah, if you look at small children who try to talk and walk at the same time, they fall. Because it's very interesting to look at small children growing up when you think of this, because they don't have the parallelism of the systems basically made unconscious. So I don't have to think about myself walking towards you while talking and think of the content of the presentation, but this is the result of a learning process that now has resulted in me as an adult being able to do this in parallel and to not having to think about this anymore. It's like driving a car, talking to your girlfriend, and so on, and listening to the radio, but still safely driving the car. And the machine, and this model doesn't at all allow for this. It only allows one step after the other. So it's actually not a model of how animals interact with nature. And now the point is, you could always say this is an argument we get very often. Yes, but there is another form of intelligence, and this is this form. This form we are mastering, yes, but it's not intelligence. It's actually, this is the reverse of the reverse formulation of the reinforcement learning problem. And the reinforcement learning problem is a task, is a method, and this is very important now, that has been designed to utilize data that contain regular patterns so that these patterns can be identified automatically. And this is what AI is mostly about. It's mostly about the ability to identify regular patterns in data and to create equations which describe these regularities in the same way that F equals m times a, which is the famous second law of Newton, describes the falling of a body under gravitation in a vacuum. And this equation is true for a feather or a stone falling in a vacuum, because on the vacuum they fall with the same speed, and the only variable that determines their speed is not their weight, right, but only the gravitational constant. And well, it's not true. The weight is of course important, but if they weigh the same, if you take a pebble, and the fact they will fall at the same speed. and have the same force while falling, and this is a regularity which Newton observed, and which he put into an equation, a differential equation, and this equation here, this utility function, or this intelligence definition by Hutter, is basically a definition that is tuned to be achieved by doing reinforcement learning. But then if you look at what these machines can learn, they can learn a lot. And I have been making a living from AI since 1998. So I'm not at all an opponent to it. I live from it, but I'm realistic about it. And with such methods, you can achieve a lot, but there's a lot you cannot achieve. Namely, you cannot mimic animal or human intelligence. Now let's look. Very important in this definition is also the R, which is the reward. And you see that the reward must be chosen in a way that the average value of the sum of all the rewards given to the system is more than one. It's basically a probability function. You can see that this looks like the integral of the Gaussian function. So the Gaussian distribution, probability distribution, also has an integral equal to 1. And so this shows you that they are trying to mimic here a standard, and all distributions using statistics have a total probability of 1 or smaller. And so this is what they're trying to mimic here. So that you have relatively small steps here of reward. But the problem with this reward is the following. This is basically the core why ChatGPT does not really work. It's trained using reinforcement learning. So it's the last training steps that are performed on it are using reinforcement learning. Why is this so? We will learn this today. I hope we still have the time, because you need a lot of training events to train it, and you cannot create those training events by hand. And if you cannot create them by hand because it's too much work, because you have many billions of training tuples you need to train it, and you need to artificially create these training tuples. And to do this, you need an artificial reward. And so the problem with artificial rewards is that they are not like the rewards you obtain in real life. So to say this in a different way, Hutter's definition restricts the meaning of intelligence to those cases that involves the summation of a series of rewards obtained in discrete steps. That's why he's not using integral, but a sum sign. But unlike vertebrates, a machine realizing the putative universal intelligence is in one sense not intelligent at all, because it relies on some human AI engineer who defines the reward for the system. So a human engineer defines the reward. Now let's look at two cases where the computer is beating humans. One is the game of Go. I used to play it a lot when I was a teenager and student. Because it's a very challenging game where you need a lot of formal intelligence. So I really enjoy to play it. It's like chess, but I prefer it because it's more abstract than chess, because there's only one type of piece, which is a stone. And it's harder to. It took, chess was solved in 1996. Solved means that the machine was superior to the human being in 96. In Go, it took 20 more years. It was in 2015 or 16. And it was done with reinforcement learning, and we cannot go into the details, but it's super impressive and a great achievement of engineering. But why did it work? It worked because in Go, you can define a reward function, which is based on the number of fields that you are surrounding. So the Go game is a grid, and you can put stones on the grid. And now if you have 4 black stones on the vertical and horizontal around this point, you get 1 point, right? Now if you encircle, well, that's a bad example. Well, if you actually manage to encircle a white stone that is surrounded by black stones, you can capture the white stone and get another point. So these are the 2 ways to get points. Either you capture a stone of an opponent, or you basically have encircled the field. And so this, with this you can define a clear reward function, and now you can use reinforcement learning, and then it can be shown in a closed world setting you can always solve the problem. And this is what they did. Now this is possible in Go. In the ego shooter example, the reward is the kill points. So you can assign kill points to an opponent. You can also assign kill points to objects that you destroy. And then you can also optimize this reward. The same is in poker. So there's a poker mode. I'm not a poker guy, but there's a poker mode online where you cannot see the opponent's face, but where only the cards that you get. So where you cannot bluff, not really bluff, because for real bluffing, you need human interaction. You need to look at the face of the opponent. If you take this away, if you have a poker game where there is no bluffing, the machine will beat the human being, because the machine is better at objectively evaluating the value of a given hand, and also the probability of drawing another card and so on. And so the computer is also closed world. And then the reward is, but for conversation, it's not possible to specify a reward. So what they did in ChatGPT is that they use 6 levels of reward, like school degrees, from 0 to 5. And the tens of thousands of engineers, mostly Indians, Pakistanis, English-speaking engineers in cheap labor countries, they had to basically, in a certain learning step of ChatGPT, they give ChatGPT is then asked to give answers to questions, and the engineers rank them from 0 to 5. And they do this hundreds of thousands of times, and then a ranking is established. And the ranking function is derived automatically. And then millions of questions and billions of questions are asked to the machine. The machine gives answers, but then it ranks the answers itself into 5 and 6 categories. But if you think of how you are ranking interlocution partner, you're not giving the ranks from 0 to 6. You have a very complicated impression of the interlocution partner that in the end decides whether you find him satisfying as an interlocution partner or not. And the same person who might be very satisfying to one of you might be totally dissatisfying to another. So it's a very, very complicated matter. And we cannot specify a reward system for this. And so therefore, all the intelligence that the machine gets depends on the reward sequence that is specified. And if it is, and so because we can only use reinforcement learning for situations where it is legitimate to specify simple rewards, it cannot be done, for example, for customer correspondence management. So if you have customer correspondence coming in, and now the neural network gives an answer, the answer will often be wrong. And that's because so many things need to be taken into account to find the right answer. Even if in a typical customer service or insurance, the answers seem, so for example, am I covered to be insured for this situation? Or what will it cost to add a child of mine to this insurance? So the questions are pretty stereotypical, but still in each case, so many aspects are required that the LLM cannot calculate. The LLM trained on such a simplistic pattern, like 6 grades, cannot be trained to find all the right nuances, and that's why it failed. It fails mainly because we are unable to set up the right reward function. And this is very critical to understand. This is why I'm spending time on this. Now, what I have here, another aspect. Let me see. Oh, yes. So basically, this is that the reward types are very the actions of intelligent agents have very different reward type from one moment to the next, because the subject interacts with the environment. The way the subject interacts may change with each act of the subject, even if it's just an act of perception. And so that means that basically that not only is it hard to find a scale for the rewards, but you may suddenly switch from R to P or Q, a totally different type of reward. So the type of reward that you get from interacting with me is very different from interacting with your girlfriend, right? And it's a totally different type of reward on a different scale and so on. And so you cannot, it's very, very hard to define this, and basically impossible to define this abstractly. Also, this vacuum U doesn't capture the relationship between the type of situation I'm in and the type of reward I'm getting. So it assumes that that to every situation that is part of the set of situations uppercase U, there's the same reward sequence applies, which is of course totally wrong. So now this was the first segment of today's lecture. It was about the Hutter definition of machine intelligence. To recapitulate this, why did I select this definition? Because it's basically the one that drives Jeffrey Hinton to believe that intelligence has been solved. He believes intelligence has been solved because we have now systems that are intelligent according to this definition, right? And that's basically to give the answer, the abstract answer to your clever question that you asked. The individual psychological answer, how you can be so foolish. I mean, Hinton is very intelligent, but foolishness doesn't relate to intelligence or stupidity, but foolishness relates to the ability to abstract away your thoughts from your emotions. So if you're foolish, you can be very intelligent but foolish, because foolishness means that you are not capable to dissociate yourself from your emotions, which is required very often to act adequately. So in a situation of being tempted to do something wrong, you need your eagerness to do the wrong thing must be overcome by your intellect, so that your intellect tells you, I have to suppress my sexual desire or my anger. These are the two main motives for foolishness, are anger and desire. And I have to, or it's not only desire for sex, it can only be desire for food or anything else. I have to suppress this desire in the interest of something else. And I think Hinton, he accepts this very narrow and wrong definition of intelligence because of emotional reasons, ultimately because he's foolish. Now this is basically the first part to give you an impression why this community believes that they already have AI. It's because they have created for themselves over 30 years a definition that they can fulfill. And if you ask Twitter, who's teaching here, he also argues that we already have AI because he has built a lot of very clever algorithms that can fulfill this definition. And I'm not, again, I don't want to in any way diminish this. This is a wonderful and major achievement of mankind over the last 50 years that has been achieved to bring those ideas, which, as we'll see, are indeed very old. So most of the ideas that support AI have already been thought of at the turning of the 18th to the 19th century, around 1800. So when Legendre and Gauss figured out regression, they had the core ideas of today, but it took them more than 200 years to flesh them out in a way that we can really use them. That's a great achievement. I don't want to diminish it. I just want to say it's not intelligent. Okay, any questions to this part before we move on? If not, let's take a step back, because we are going to argue that all the AI algorithms are models. And to see what this means, and when you had a logic course in computer science, there a model is actually something that makes a sentence true. So we use model in a different sense. I want to make clear what that is. So in Cartesian sciences, so with Cartesian science, I mean all the science based on mathematics. A model is a representation of an aspect of reality using abstract symbols that is created to describe, explain, or predict the aspect of reality in question. For example, F equals m times a is a model of gravitational force, or a force based on mass in general. An adequate model then is a model that relative to some set of requirements can be used to engineer an entity or an emulation that satisfies all the requirements in the set. So you have a set of requirements, and now an adequate. So if you want to build a bridge, you have the models of statics, right? And with the models of statics, you can actually build a bridge that satisfies the requirements of the set. So this is what you get. Or if you have a turbine, you want to build a turbine, and now there's certain, how much the turbine should accelerate, how much fuel it should use, how hot it should get. And now you have equations, Navier-Stokes equations and other equations that are used to build turbines that allow you to fulfill. This is an adequate model. A synoptic model of a system is a model that can be used to engineer a given system or to emulate its behavior. So that means, for example, a synoptic model for human intelligence would be a model of human intelligence that would allow us to make a machine that is really as intelligent as a human being. And here on the right-hand side, you see some models of classical mechanics. So on the top, you see the phase space of an ideal pendulum, which is completely defined by two magnitudes, which are velocity and position, right? So if you have the velocity, or you can also, instead of velocity, you can also use acceleration or a P, which is impulse. What is it in English? I remember it. You can also use, but basically this is a phase space. It defines totally the behavior of the system element with two coordinates in this case. It's one of the simplest models. And on the bottom you see trajectories of a missile launched at different elevations against elevation angles, but the same speed in a vacuum. So these are ideal trajectories of missiles. And there are if you use these trajectory equations in the real world, they are quite adequate, and they are the equations there are differential equations used to calculate, for example, the trajectory of an incoming missile in an air defense system. And so these are examples for synoptic and adequate system, the models. Now, Barry already told you something about simple systems and how they can be engineered to work reliably. So this is very important. So when we engineer something, like if you want to do AI, we need to, this will be a system. And from the perspective of thermodynamics or system theory of thermodynamics, classical logic systems, they have the following properties. They have no evolutionary character. That means, think of the solar system. The solar system as a gravitational system is almost a logic system. It's not completely, but it's almost a logic system. It can be modeled quite well as a logic system. It can have new element types. It can have new elements. For example, a new asteroid can get into the orbit of the sun and start circling around the sun because it's attracted by its gravitational force. But because its momentum is conserved, P is momentum, that's impulse. What is German impulse? Is momentum. Because momentum is conserved, it will continue to circle. It will not fall into the sun, because as it reaches the gravitational influence sphere of the sun, it will still have its own momentum, and therefore it will get into an orbit. So this is a new element, but not a new element type, because all the planets are already satellites of the sun. So the solar system as a gravitational system can get new elements. It can also lose elements. So an asteroid, might because it has friction, so it might be used up because of the friction while it's flying in space, and then at some point it might be extinguished. Its matter might be used up, transformed into energy, basically. So it might, like a comet, it might be used up. And then it will vanish. But basically, the element types are the same. So this is the first property. Then the interaction types are uniform and isotropic. So that means that if you have a source of energy, like a heat source, like the sun itself as a heat source, the heat is propagating in the same way in all directions and also in a uniform way. Also, in the gravitational system of the solar system, you have only one force that is responsible for the behavior of the planets as satellites of the sun. That's the gravitational force. So remember Newton's first law. The momentum of the planets is conserved, so they have their own momentum. And this is interesting because the momentum they've had for billions of years now. Right? This is why the Earth does not fall into the sun, because it has its own momentum, which acts against, which is centripetal, so centrifugal, so which acts against the centripetal force of gravitation. And so that's why it can have an orbit. But that's the only force that counts as gravitational force. It's the only force that you need to understand this logic system. Also, the phase space of the solar system is deterministic and ergodic. That is very important. Deterministic means that it can be formulated using laws. It's regular. And ergodic is a key term that we're going to use in this lecture. So ergodicity means that the probability of each component of the system everywhere in the system is the same over time. So now if I take this bottle of water, and now there is, of course, carbon dioxide in this water, but if there would be no carbon dioxide, the bottle would be isolated against, in thermodynamics we say isolated against its environment. It would not move, and the temperature would be constant, and the pressure would be constant. Then the probability of finding a certain particle anywhere in the bottle is the same over time. So that's an ergodic system, and that is, so to speak, the optimally regular system. And the solar system is regular. So basically it's predictive. You can predict at very, very high precision where the planets will be in thousands of years. You can predict all the solar eclipses for thousands and thousands of years because of this. Because the system is ergodic. Why is it not really a simple system? If you think of this, the sun, and here is, for example, the Earth orbiting. The Earth is actually not following this trajectory, but the trajectory of the Earth is like this. So it wobbles a little bit on its trajectory. And the wobbling on the trajectory is not modeled by the Newtonian equations. And the wobbling of the Earth on the trajectory is the result of the attraction of Mars and other planets that is acting on the Earth. So not only is the sun attracting the Earth, but the other planets as well. And depending on their position towards the Earth and the sun, the attraction force varies. And therefore, this wobbling is different every day, even every second. So the wobbling is totally irregular. And so this is very, very, very hard to estimate. There's no analytical solution for this wobbling. So you cannot write down a system of partial differential equations that describe it. You can simulate it in a computer, but it gets very, very difficult. So this is a complex property of the system, which comes from the overlay of the gravitational fields of the sun and the other planets. So when you have overlay already, so that's why if you look at it closely, the solar system is not really a logic system, but Newton's approximation is very, very good. And so it's almost a logic system. But what this shows to you is that no natural system is a logic system. They are all complex systems, even this one, though the degree of complexity is low. very importantly, it's not a driven system. So what is a driven system? The sun itself, as an electromagnetic phenomenon, is a driven system. So as a gravitational phenomenon, the sun is only gravitational because it has a huge mass. The gas out of which the sun is made is a huge mass, and this mass is producing gravitation. That's why but as an electromagnetic system, it's a fusion reactor, a huge fusion reactor in which all the time hydrogen molecules are transformed into helium molecules. And this process of fusion creates energy, and it creates a lot of energy. Because it's interfering with the forces that hold the nucleus together, and so it creates much more energy than nuclear fission, right? Therefore, it's the as an electromagnetic system, it is driven. So it means there's a flow of energy through the system. So all the time, energy gets released from the system in the form of highly accelerated photons of a broad spectrum. And these highly accelerated photons, then we can measure them as electromagnetic waves. Some of them are visible today. We see only the part that is filtered through the clouds. But basically, this is energy coming from the sun. And as such, it is a driven system because there's a flow of energy through it. This bottle is also driven. The contents, because you can see that from time to time CO2 bubbles are arising in it. That's because there is no saturation of the CO2 in this part of the bottle, and the liquid part has a surplus of it, and so the bubbles are rising and transforming into gaseous form of carbon dioxide in this bottle. And so this is also a driven system because there is a transformation process going on. And the reaction is actually exothermic, so a bit of energy is produced when this is released when this is happening, and otherwise it wouldn't happen. And so this is a driven system. If I shake the bottle, which I won't do because I want to drink the carbon dioxide containing water, then much more is going on. There's much more drivenness. We are all driven systems because we all the time make energy inside ourselves and consume it. But the solar system is not a driven system. There's no transfer of energy. Also, such systems have fixed boundary conditions. So that means if I take the solar system as a whole and put it a tenth of a parsec closer to Alpha Centauri, which is the next star system in our galaxy, which is next to us, then nothing will change. Because as long as I don't have an interaction of the gravitational force of the two suns of Alpha Centauri with my sun, I can shift our system. I mean, we will get new satellites and asteroids coming to us if we are in a different position in the galaxy, but the gravitational system would not care. That's called fixed boundary condition. But if you put a human being under the water for 10 minutes, good morning, then the human being is basically dead and will not work as a system anymore. So we don't have fixed boundary conditions, but classical logic systems have. Also, chaos. So chaos in the sense of physics is everywhere. Chaos means that you cannot, so it's called deterministic chaos, it's a chaos theory. And it means that if you have a partial differential equation that perfectly describes the behavior of a system element, now you measure the initial conditions of the system element in the universe or in the system. Like I put in a radiator system, I put a piece of wood that can swim in the water downstairs in the central heater. We have all the equations to calculate where the piece of wood in which radiator it should end up, where it should go when, but we cannot calculate it. And that's not because we lack the equations, but we cannot determine with sufficient precision the initial conditions under which the piece of wood will be. So, and we can, if we measure, we have a measurement error, and this measurement error, because of the multiplicative effects of the solutions to the Navier-Stokes equation, they will multiply up, and it will not be possible to predict where the piece of wood will be in the system. That's called chaotic behavior. Now, if you think of a steam engine, it works with heated water that creates pressure with water vapor that then moves part of an engine that moves in the end the train that is driven by this steam engine. If you think of such a steam engine, the steam engine is a simple deterministic system, although it contains chaos. Because when I heat up the water in the boiler of of the steam engine, I don't know which water molecule will end up as vapor at what time. Over time, they will all end up as vapor. Therefore, the engine will have to stop and the water will have to be refilled. But I cannot predict which molecule will go first because I have deterministic chaos in the water container. But this chaos that is everywhere in nature, that is just to do with our inability to measure systems with sufficient precision. And that's how it was discovered. It was discovered with rockets in the 60s who failed. And these rockets failed because the computers inside of them were only computing the trajectory at 6 or 7 decimals behind the comma precision. And because of this rounding error, they lost the trajectory and exploded. And then when it was analyzed, why can one of you close the door, please? When it was analyzed why this happened, it became clear that it was a lack of precision of management. That's how chaos theory was set up. And so, but and we have also, as I pointed out, this can also be, this is not a phenomenon of chaos, but we have many simple systems. We have chaos also in every combustion engine. We have it, but the chaos doesn't have any influence on the behavior of the system. So though they are chaotic, the chaos is not relevant for the behavior of the system. These are the properties that allow us to engineer. Everything we engineer needs to have these properties. And natural material, natural systems don't have this property, right? So when we engineer classical systems that we can control, we need these properties to be present, otherwise we fail. So when simple systems get out of control, they become complex systems and acquire some of their properties. So here we see the explosion of a steam engine in Texas in 1896. And you see that the coal that was in the engine has a energy density of 40 joule per liter. And then here we see the explosion of Chernobyl. It is, by the way, it is a docu-fiction from 2019 about Chernobyl that was made by the BBC and the Russian television. At that time, they were still working together. Now they don't anymore. But it is, if I can recommend something to you that has nothing to do with what we are teaching here, you should go and watch this documentation. It is absolutely fantastic. So if you search for HBO Chernobyl 2019, you will find it. It's a 6-piece, it's a mini-series, because you learn so much about power. How in human relations, power, I mean, Chernobyl only happened because some idiots in the Communist Party wanted to be acknowledged by even higher ranking idiots in the Communist Party. It's just, and all the engineers were totally against this. And they basically, it only happens because you should watch the video. It's fantastic in many regards. And here you see a still from the explosion, and you see that the energy density of uranium is 1.5 times 10 to exponent 9 joule per liter. So it's 30 million times higher energy density than coal. And if you now would take hydrogen in a fusion reactor, it's another 1,000 times higher energy density, right? And so this is just a side remark that the devastation potential is proportional to the energy density of the burned fuel, right? But this system, these two systems were simple systems. Even the Chernobyl, even an atomic nuclear fission reactor is a simple system because though it has a flow of energy through it, right? So it's a driven system, which is also true for combustion engine. The drivenness is under control because the drivenness can be regulated. So we have modulators that modulate the number of neutrons flying around in the reactor, and these determine the heat that is produced, and the heat can be measured then on the turbines that create the electrical current. In the end, we can exactly calculate how many neutrons need to fly around in the reactor to create a certain amount of watts. And the same is true for combustion engine. We can exactly calculate how much fuel you have to inject into the combustion engine to create a certain Newton meter acceleration torque force on the wheels of the car. And so this is so although there is energy dissipation and flow of energy through the system, it's still a simple system. And here it loses its property suddenly, which is a very interesting process. By the way, if you look at computer systems of large administrations or of big companies like Novartis or any big company, they also like this. They have been planned and engineered as simple systems, but now they are out of control. And so that's why it is very, very hard to change them. And that's why it always costs many millions or billions of companies to change big computer systems, because they have lost their ability, they are failed systems, they have lost their properties as simple systems. And that's why engineers, by the way, engineers always want to engineer so that the system is kept simple. They always insist when talking to the CPUs, no, we shouldn't do this. If we do this, we lose one of these properties. So engineers are very aware of these properties. They always want to keep them. It's also my job, in my day job where I make money with to feed my family. I always insist that I want to keep those properties to be as close as, because that means success. And if you are deviating from them, try to do something outside of this, you immediately fail. And we shall see now why. So why do we fail? So here, I'm again looking at the properties of complex systems. Now I'm contrasting, and I'm going through the 7 properties again that why is it not reacting anymore? That I had here, but now for complex systems. So every natural system is a complex system. So here you have a fly, which is an animate complex system, and below that you have an inanimate complex system, which is a water cycle, which is a very big system that creates the clouds and the whole everything, all the water that we see in nature is dominated by this water cycle. Now we can look at how they differ from simple systems. Now the first property is the evolutionary character. This is fascinating. So evolutionary character means that not only can you have new elements, but different element types. Now, what's an element type? So, for example, a bacterium can acquire that has a chromosome. Classical bacterium like Escherichia coli has 1 chromosome, and you would believe that all its functions are based on this chromosome. That's true. But if you feed it enough with antibiotics, it can acquire a plasmid. A plasmid is a small metachromosome. It's a small circular piece that encodes for a gene that can provide antibiotic resistance. Now, the wild-type bacteria that you see in in the normal wild, they don't have these plasmids. They have just their chromosome, and so they acquire a new element type. In language evolution of human language, we have new element types all the time. For example, a novel usage of a case in a syntactic case is a novel element type. So complex systems can create not all new species that diverges from an old species. So evolutionary systems can create new element types. And so what does this mean mathematically? Well, mathematically, every element type corresponds to 1 coordinate in a Cartesian system. And so, as you know, we have the one that you all learn at school is 2 dimensions, and if you study mathematics, you learn k dimensions. You learn multidimensional systems. Mathematicians describe them using a matrix. Right, so the matrix, the columns of the matrix are the coordinates of the system, and the Cartesian system you learn at school has just two columns. The 3-dimensional system, some of you may have seen as 3 columns, and then you can have much more columns. And for example, the ChatGPT has 2 exponent 10 or 12 columns, so it has now, I don't know, maybe it can digest, it can encode a language in a vector with 2 exponent 12 type elements, so that is a very broad matrix. And Ernie or BERT, which were the first neural networks dealing with language, I think they had 512 or 1024 such elements. And now they are making more, but that requires more computation power. The problem now is that if you have a new element type, you need a new coordinate. I give you an example. When in 2014 for Allianz Health Insurance, I built an AI system to classify, so when they get the claim for a hospital patient, 70% of the claims they get are okay and can be paid out. But 30% of the claims contain elements which should not be paid because they are fraud. I mean, the hospital is exaggerating what it did to get more money for the case. It's a business model. It's everywhere in all insurance systems of the world. There's moral hazard, and those which use the insurance system try to claim more. Also the hospitals, because they are competing for profitability. So they hire consultants, and the consultants, they do what is called upcoding. And so when I worked there, there was an outbreak of bird flu. And the outbreak of bird flu made the cases that had bird flu more expensive, right? Because bird flu is harder to treat. A human infection with bird flu happens rarely, but when it happens, it's harder to treat than regular flu. and it takes longer to treat, so the case becomes more expensive. Now the system failed on these cases. It failed to classify them as cases that need to be checked by a human claims manager. And I analyzed this, and I put in a lot of thought, and then I found out with the help of two associates that basically we were not capturing this property, which this property didn't exist in the diagnostic catalog. So the diagnostic catalog didn't have an entry for bird flu. When we added a column to the margin for bird flu, the performance of the system was repaired. So we have to expand the vector space of the system ourselves to make the system work again. This is the effect of a new element type on the system. The system cannot find out itself that it needs a new element type. So the engineer needs to find out, which may be very difficult. So in this case, it was very difficult. We had to filter down the cases where there was a difference and then look at them. And then at one evening, I said, no, well, these are all what we have. Of course, they all have bird flu. Then suddenly I realized that this is human intelligence, by the way. Then I made a bird flu column, we encoded it, we made a new mu variable for this environment, like you saw on the Hutter equation, and then the AI worked again. And so this is the first thing. So when systems have evolutionary properties, they cannot cope with it because the evolutionary properties create an irregularity. Second aspect are the element-dependent interactions. So laws of physics always need uniform and isotropic mono interactions. This is true if you look at the Schrödinger equation, which is a very important modern equation of quantum physics. It can always, each Schrödinger equation, the abstract Schrödinger equation can cope with different variables. But if you want the Schrödinger equation to apply to something, like momentum, or location, or vibration, for example, or angular momentum, every time you need to write down the new version of the Schrödinger equation, which deals with this type of interaction that it's now supposed to describe. So there is no general Schrödinger equation, but you need a specific Schrödinger equation for everything you want to describe. And so that means, good morning, that means that we have that we need in physics always uniform and isotropic interactions. That's the same is true for the theory of quantum fields, but for classical mechanics, for general theory of relativity. And so if you have element-dependent interactions or force overlay, you get non-classical laws. Now, you don't get laws anymore, right? It would be the better way of saying it. And now, what is an element-dependent interaction? So an element-dependent interaction is an interaction that changes depending on the element that is involved in the interaction. You have this in language all the time. When you take any word of language and use it in different contexts, it changes its meaning. So the words interact in the sense in a different way to give the words different meaning. This is an example of element-dependent interaction. A force overlay means that you have several forces working at the same time. So you know that in physics, we have the theory that we have four forces determining everything in the universe: the weak force, the strong force, the electromagnetic force, and the gravitational force. Three of them have been put into the unified model, which is basically our current view of matter. It's called a standard model of quantum field theory, and it can deal with the three forces. The force, gravitational force cannot be dealt with. Together with them, it's separate from them. But basically, these four forces need to be independent. So, for example, when I asked myself about what's happening to a piece of mass in the vicinity of a black hole, I can look at it either using what is the standard way of doing it, Einsteinian field tensor, which is general theory of relativity, to understand what's going on, or I could try quantum mechanics to understand what's going on. But I cannot do the two at the same time. So when I use quantum mechanics, I would probably, in this case, do electromagnetic interactions that are described as quantum mechanics. But when I do a general theory of relativity, I use gravitation. But I cannot overlay them. But in reality, it's quite clear that both play a role at the vicinity of a black hole. But physics cannot deal with it. Physics can only model uniform interaction types. But of course, in complex systems, all the time, all the forces interact. And that's why the equations we can set up to describe physical systems are always very partial, because they only address one force type. And this is also true when we train AI, which I will come to later. Now, the next property is my favorite one. And this is very, very important for you to understand the limits of AI. So the phase space of an ideal pendulum that I showed here is ergodic. So if you think there's no friction, so this in the ideal pendulum, the pendulum is frictionless. It's suspended there, it's a suspension point, and the sine and cosine wave, or it's two sine waves, but shifted. The two waves that you see here, they are basically regular forever. So infinitively, the pendulum goes like this, and so the probability of the pendulum to have a certain velocity and position over time is uniform, which you can see from that basically the phase portray, which portrays velocity and position against each other, is circular, and so the position of and momentum of the pendulum is on a circle, so that means, and its probability to be there is every time over time is the same everywhere. So this is ergodicity, and complex systems are not ergodic. So they basically there is no regularity that can be modeled as a law of physics, and no representative samples can be taken to train implicit models. This is very crucial. So let's look at turbulence. So if I take this bottle now, I will shake it a bit, but not too much. If I shake this bottle, I introduce force onto the mechanical force, and this makes the molecules move. And this movement is called turbulence. So there are vortices forming in the bottle. So if I shake it a lot, very well, then a vortex forms. The same happens when you have a bathing tube and you let the water out, you will see vortices form. Now these vortices transform mechanical energy into heat. Right, so this is called energy dissipation. The mechanical energy of the draining water it is transformed into heat by these vortices. And there is no mathematical model for this because it's an irregular thing. Heisenberg, I think Heisenberg, along with Einstein and Planck, is the number 3 greatest physicist of the 20th century. It's incredible what he did. So when he was already older than 80, and the unified theory of matter was brought forward in 1976, he contradicted it. He contradicted the theory of the quark. And as we show in the second edition of the book, he did it in a way that could not be repudiated or not be invalidated until today. So his argument against the theory of the quark is still valid today. And he did this when he was already over 80, an incredible genius. Once he was asked what questions he would ask God after he would die, and what answers he would like to be getting. He said, well, so when I will die, I will first ask for what is really the nature of gravity, because we don't know. We have no graviton, we have no particle that explains gravity. We have particles for the small force, the weak force, and the electromagnetic force. These are called the bosons. So we have particles that we can use to mathematically describe these interactions of matter, but we have no particle for gravitation. We don't know what is actually mediating gravitation. It's quite fascinating. It's such a basic phenomenon we don't know. And he said, I'm certain that God will explain this to me, but as to turbulence, I will ask what about turbulence? God will say, I don't know. And so this is a joke, but he used to tell the students, but to make clear that we have no idea how turbulence works. And that I don't know any serious physicist who claims that we will ever. And so that's because turbulence is a phenomenon of non-ergodicity. That means that if you look at the waves at the shore of the Mediterranean, here you drive by car to the Mediterranean shore, you look at the wave patterns, they are always different at the microstage. At the level of the molecules of water that form a wave, there's never a regular pattern. Even if you disregard the identity, of course, the identity of the molecules, it's trivial to say that the identity of the molecules is different. But now if you disregard the identity and say, I don't care, every molecule of water is the same for me, even then, there is never a regular pattern. So for billions of years, we could make movies of these waves. You will never see a regular pattern. Of course, if you listen to them while falling asleep, it sounds very regular. Some people like to fall asleep. But if you look at it, at a micro scale, it's always different. And this says no regularity. Now comes the important thing. When you do AI with stochastic methods, you are training AI to extract the regularity out of a pattern. But if there is no regularity, you can forever draw samples of the distribution. You will never get a regular distribution, and you will never train the AI. And it's 95% of the failures in the AI field are based on the lack of insight of engineers like Hinton or Musk into this problem. that many of the systems we are looking at don't have a regularity. So it doesn't matter how long we sample. We don't get an improvement. That's why ChatGPT is not improving anymore, because the regularities that can be taken from the language stored on the internet have been fully exploited. There are, of course, regularities. I don't want to neglect them and ridiculous. They're great. I mean, I'm using Google. Actually, the presentation I'm going to give tomorrow was originally written in German. Now, because I get bored of presenting the same stuff, I wrote a lot of new pages in English, but the first 20 pages were in German. I just also translated them. Now, because now, since a couple of weeks, there's the translate function is built into Microsoft Power. It's great. You can just click translate, and it saves so much work. You know, in the olden days, I actually hired translators to translate my texts, and now, because I didn't have the time to do it myself, and now it's just I just click on translate, and then the effort of correcting the translation is still higher than if a human translator has done it, but it's not, it's negligible. Right? It takes a couple of minutes just to check the whole, or 2 minutes to check the translation of the slide. And so this is great achievement. I don't want to diminish it, but I want to say that the regularities that are present in computer stored language are now used up. And then once they're used up, you don't get an improvement. And this is what many people don't see also in pharmacology. So that's my specialty, right? My job is to find new ways, new molecules to treat cancer. So I'm not only finding new small molecules, that's the ultimate goal, but also the proteins, identifying proteins in cancer cells that are amenable to drug treatment. And once I've identified such a molecule, I find chemical ligands that bind to it and inhibit the molecule. And for doing this, I try, of course, because I'm an AI specialist, to use as much as AI as I can. But the percentage of the problem that is amenable to AI is super small. And that's because in the interactions of the protein, which now I draw like this, right? This is a protein, and in the protein you have a pocket where the function of the core function of the protein is happening. For example, the protein uses ATP and makes out of this ATP, and by this it can add a phosphor group to another protein. That's called kinase function. So here's a phosphor group, adenosine triphosphate, that's adenine diphosphate. So one phosphate group of this molecule gets removed and gets put into this molecule. And this is basically the form of energy of the cell. So energy is consumed to phosphorylate. And here is the kinase domain where this ATP is bound. And now I want to inhibit this, and I want to do this by placing here another molecule, right? That basically makes it impossible for this protein to bind the ATP. Now people have tried since the 80s to use AI to predict the shape. It's failing. And it's failing because every ITPase, every kinase is different structurally from the other. And so you cannot do that. So although it looks as if it would be simple, they are also different geometrically that you cannot predict using computers. You cannot exploit any regularity. And so there are other methods that you can use, which we are also using, which also accelerates this process. But overall, AI is not amenable to this problem because there are too many combinations and because it's a non-ergodic problem. And so that's when you cannot draw a representative sample. Let's take another counterexample. If I want to know the average body height of women and men in a southern European population with some migration factor in it, I can go to Lugano and sample 1,000 women, 1,000 men by chance. I get a small bias if I sample them on the street because older people don't walk around so much, but basically body size is not so strongly age correlated, it's just a few centimeters. So I can sample, I can measure female height and male height, and then I get a very good approximation because there's such a regularity because women are not as tall as men are on average. So there's a very, very important correlation that I can find is super regularity. And when I build AI system, I always have to work with the regularity. So non-ergodic systems still have regularity. So all of us have slept tonight. Maybe one of you did a big party, but it's unlikely on a Tuesday morning. So all of us have slept and all of us need to sleep regularly. And because of the way society works, most people do this, I would say, between 1 a.m. and 5 a.m. in the morning. So there are some who get to bed late, others get up early, but between 1 and 5 a.m., usually everybody is sleeping. And this is a regularity. Everybody is breathing 20 times a minute. If you run, it's more. If you sleep very deeply, some people have a problem that they stop breathing and then they breathe much more afterwards. But basically 20 times a minute, and these regularities are there. These regularities can all be exploited. And my job and our job as a serious AI people is to look for these regularities, to create data sets that contain the regularities, and then to systematically exploit them. That's what I've been doing over the last quarter of a century. It pays very well, it's great activity, it's very satisfying, but it has nothing to do with creating intelligence. Now, drivenness, next property of complex system, is this transition, the movement of energy through the system was talking about. So I use a simple example of shaking the bottle, and when such energy transfer happens, and the energy transfer also happens in simple systems like a combustion engine, because the combustion engine, I do not know which molecule of benzene is going to be burned up next. I'm burning the benzene that is inside that is injected into the cylinder when I ignite the benzene, which is what's happened in the combustion engine, but I don't know which one will, for example, react to carbon dioxide and water first, right? I can't tell. It's a chaotic process, but it doesn't matter. But if the drivenness matters to understand the system, then I have a problem. So here, this system is driven because of the sun. So the sun is providing energy to our planet all the time. This leads to evaporation of water. Then it condenses somewhere, it drains down again, and this drives the water cycle. If the sun would stop shining, the water cycle would stop as well. All the sources would, after a very short time, the source of water would stop giving water, and the whole water cycle would stop. It's so completely driven. But because it's driven, it's not. We can only model it to a very, very superficial extent. So there is no convincing model of the water cycle because of its drivenness. So whenever drivenness is decisive to understand the system, it's a strong modeling impediment. The next property is context dependence. So classical laws need context independence. It's also called symmetry in physics, and it's very interesting. So that, for example, the law of gravitation, or let's say the angular momentum. So if you take a body and attach to a strand of rubber, or also an inelastic strand of material, to a cord, and you spin it around, you get angular momentum, right? And it doesn't matter where you do this. If you do this in a non-gravitational environment, it's the same. The angular momentum is the same in a gravitational environment. So this is a classical system which is context independent, and complex systems are context dependent. And when you have context dependence, you usually cannot derive any physical laws. So this is much harder, and the physical laws you can derive are cover much less. So that's something that many people are not aware. So let's take again the example of the solar system. So the solar system is context independent as a gravitational system, as long if you move it around in the galaxy, we will not notice, unless you move it so close to the next star system that our star and the stars of the other system will have attraction to each other. Then it's a disaster, because then the system becomes context dependent and the models fail. The models that we have of our solar systems, they are only valid if it is invariant to its position. If the position of the system becomes invariant, is the keyword I was looking for. That's the keyword from physics. And that's actually Galileo already saw this, right? He already spoke of this invariance, and it's also called Galilean symmetry. And so it doesn't matter if you turn around the solar system, if you shift it, if you do anything with it, if you put it at half of the distance closer to Alpha Centauri, unless you put it very close to Alpha Centauri so that the gravitational force will matter. And then you get context dependence, all the laws of physics will break down. Also, if the chaotic behavior of the system is relevant for its overall behavior, then also you cannot model it anymore. And so this is very important for you to understand. Fundamentally true, and will still be true, because the way physics and mathematics work, if you really take the time to understand it, it's all based on these regularities. And if you read any textbook of physics, how it works is usually an experiment that gets described, and then the laws of physics are derived from the experiment. And this experiment is set up in a way so that you can at the end achieve a differential equation. So the experiment is always simplified to an extent that allows you to derive a differential equation. if you have a natural phenomenon outside of the experimental room, you can also describe it with physics, but then you need to make a lot of assumptions. So when you read text, why I can just read Feynman's lectures on physics, which are fantastic. It's one of my favorite books. And if you read them, you will always find at the beginning of each chapter a system described, and then it says, now we know that we cannot calculate anything on the system. So let's make the following assumption to simplify the system until we are ready to calculate with it. And then comes a whole page, a half a page of simplifying assumptions that reduce the system to an artificial system about which we can make the assertions of the laws of physics. Nancy Cartwright calls this physics as a theater. So basically that you are basically simplifying nature until you can calculate with it. But lay people don't see this. For them, it's a miracle. We have, well, I can call my sister down in Australia. I mean, I don't know if it's the right time now, but I can anytime call her and so on. It's fantastic. And this is because we are mastering physics. So as a layperson, you tend to think that it's limitless. But if you have to treat cancer, you see that the limits are very tight because the cancer is a complex system within a complex system and it gets very hard. So this is very important for you to see that this is very sound knowledge of thermodynamics and has been developed in a very detailed way. These are the negative results of physics I was talking about yesterday, and summarized into one page, right? And these are very often not taken into account when the possibilities of mathematics and physics are discussed. But if you look at it carefully, I mean, nobody can basically, no mathematician and physicist can contradict to this. All of them will agree that yes, these properties prevent the holistic modeling. You can still have partial models. So there are good models of human sleep cycle, the human breathing cycle. There are excellent models of the electromotoric activity of the heart. So there are many, many aspects of complex systems that can be modeled indeed. And whenever that's possible, you can also find good ways to manipulate this. So, for example, we know that diabetes type 1 is a result of insulin, of a lack of insulin. So we can inject insulin. However, all the patients who have diabetic type 1, even if they get insulin treatment, they will all still suffer from side effects of the diabetes over time. Why is this so? Because the real pulsatile levels of insulin production, also glucagon production, are not understood. So we only give, kind of a bite. So in reality, we have a very complicated curve of insulin secretion, which maybe looks like this, But what we do is give over the day with the insulin that we inject just bite doses, And these bite doses, they prevent the patient of dying from diabetes, but they don't really cure the disease. And so this is a typical example of the discrepancy between our models and the reality. So our models are always under-complex. They are never really satisfying, and every physicist knows this. And it doesn't matter. Why doesn't it matter? Because once you have derived laws of nature, by simplifying nature to an extent that allows the setting up of differential equations, then you can use these laws to build technical systems. And these technical systems have fundamentally changed the way we live. So it is a blessing that we have this mathematics, that we have this engineering capability, that we have this limited insight into nature, but it is very limited. And we should not forget this. And we are reminded of this when simple systems become complex and get out of control, or when we are faced with the real serious reality of complex systems in any way, and are asked to change it. Now, here's Immanuel Kant. If you are studying philosophy, there's always a decision how much time should you spend on the classics. And some people believe that you should, all the analytical philosophers will tell you that it doesn't matter, the classics don't matter, that you can start with Wittgenstein and then you have only one century to cover. Then you can read all the Anglo-Saxon American philosophers, analytical philosophers, and then that's all you need. I disagree. I think that I call analytical philosophy D-Day philosophy. So it was a philosophy implemented in Europe when America won against the continent in the Second World War. But if you want to read only some classics, and I think you should if you're philosophers, and even for non-philosophers, it's very useful. Immanuel Kant is one I can recommend. I can also recommend Aristotle and a few others. But basically, if it's only two, it's Aristotle and Kant. And Kant saw already in 1790s the impossibility to model biologic systems using physics. So you have to know that he was a physicist. He worked, his chair in Königsberg was first for astronomy. So he was teaching Newtonian mechanics. And he was not a genius at this. He was okay. So he wasn't teaching the students any nonsense, but he wasn't an innovator in this, right? There were others, so for example, Lagrange. He was also doing Newtonian mechanics a couple of decades before Kant, and he innovated radically Newtonian mechanics because he set up a new notation for Newtonian mechanics that allows to calculate much better the motions of particles. Kant was just a normal user and was teaching it, but then in his 40s he became interested in philosophy and started to work as a philosopher also. And when he was already an old man, above 60, he wrote the Critique of Judgment. This is paragraph 75. For it is quite certain that in terms of, I translated this, I tried to, it's very hard to translate. But when I read Kant and have to present it to an English-speaking audience, I always translate it myself. For it is quite certain that in terms of merely mechanical principles of nature, this is what we call today physics. At that time, it was called mechanical principles, and now it's a bit broader, but that's what's physics. We cannot even adequately become familiar with, much less explain organized beings and how they are internally possible. An organized being is animate nature for him. So for him, inanimate nature is unorganized, and an organized being for him, as he explains further before in the text, is an animate being. With organized, he means actually that they have an internal force which works, and then that is what we call drivenness in physics. So an organized being is a being that transforms energy by itself, right? Whereas dead matter cannot do this. Dead matter cannot transform energy. Dead matter can only, well, there's energy transformation in dead matter, but in an organized being, there's a system of systematically creating energy from matter and sustaining the existence of this organized being from this process, which is, and also enabling reproduction by doing this energy transformation. And so sperms cannot move without ATP, right? And ATP has to be made by mitochondria and so on. And neither can oocytes live without ATP and accept the sperm. And so this is what he means by organized beings. So certain is this, that we may boldly state that it is absurd for human beings even to attempt it, or to hope that perhaps someday another Newton might arise who would explain to us, in terms of natural laws, unordered by any intention, how even a mere blade of grass is produced. Rather, we must absolutely deny that human beings have such insight. So this is a very, very bold statement. Kant was a fanatic of delimiting human intellect. So at the time of the 18th century, there was a huge euphoria already about the possibilities of human intellect, because when Kant lived, big philosophers like Voltaire and David Hume had given up. They said that God doesn't exist, and that the only thing that matters is the human mind, and that the human mind is capable of everything, which is basically what Jeffrey Hinton and Elon Musk still believe today. And also even worse is Yuval Harari. And Kant was much cleverer than these people. He said, no, actually the human mind is very limited, and he devoted the last 2 decades of his life to trying to define the limitations of the human intellect. And if you look at what he did also in the Critique of Pure Reason, he of course didn't foresee general theory of relativity or quantum mechanics, but what he says about the limitations of human mind is still absolutely valid and fascinating. And of course, Kant didn't have any proof for this statement. And I also don't have a total bulletproof proof for this statement here as well. But it is totally implausible that can model complex systems comprehensively. And yes, and he already saw this very early on. Now there's an aspect to this which is of course classical metaphysics. So Kant believes that organized systems are driven by an intention. This is of course something that, and this intention, he's not saying that it's God's intention, but they have an intention. It is what Aristotle calls entelechia. Entelechia means in Greek the built-in goal of the organism, that the organism has a certain goal which is built into it, and that we don't understand this entelechia, but that is driving the organism. Like the sunflower is turning towards the sun, that's entelechia. Yes, please.
Just about what you were saying, will it be reasonable to understand the intention that you just mentioned as cause, but cause in terms of the Greek word telos, as a reason of happening, a reason of being?
So telos is not causing. Telos, I studied actually at the university. Telos means go. So it's not cause, right? But still, what the intention is directed towards the telos. That's true. Yeah. And so now intention is very important term in Husserl's philosophy, because he believes that our way of dealing with the world is based on intentionality, which is directed attention to things. So yes, so it's related to the goal, and organisms have goals. The two major goals are survival and reproduction, and these goals, that our attention are always directed to them. In the lower animals, this is quite immediate. In higher animals, it's very complicated, and then so that it gets to the point where you can have such cultural events as this event, which are very far away from survival and reproduction, but which are still somehow related to it. Now, because I can feed my children because of this work I'm doing and so on. So Kant saw this very clearly, and he saw it because he realized that there must be properties of the natural systems which makes them radically different from technical systems and also inanimate systems. Now, I would like you to give you the opportunity. So, because this is the core of the book and so important, I would like you to give you the opportunity to ask questions about this. And what I find fascinating is that nowhere where I have presented this have I ever met anyone who could really contradict it. No physicist, no mathematician, no philosopher. It's fascinating, and I'm not saying this because I have invented none of this. This is all, the results of thermodynamics. But no one has applied it before to the question of whether AI is possible. But if you have any questions on these terms, please ask now before we proceed. Yes.
Probably there are super naive questions.
It doesn't matter.
First is, how are we defining regularity?
So regularity means that that a pattern periodically occurs over time, and that when this is happening, that the pattern periodically occurs over time or over space. So if you have a static entity which doesn't change over time, then the regularity is a pattern that is embedded in the structure of the entity. Like, for example, sodium chloride ion is regular because we've always, there's this grid of sodium and chloride ions. Or the structure of frozen water is also highly regular. Well, no, that's actually not a good example. Let's stick with the sodium chloride. Because frozen water is really difficult. Water is terribly difficult. But sodium chloride is a good example. So there you have, and the regularity over time is a good example. Is the sleep wake cycle. So these are when patterns are stable over time.
Okay, and according to your answer, how do we set the parameters in order to evaluate if something is regular or not? Because if you are saying that it's over a certain amount of time or over a certain amount of space, to say it so, we need parameters to kind of.
Yes. So this is a good question. So, for example, few people know that there is a galactic day, a galactic year. The galactic year, I think, is 120 million Earth years. So this is the time it takes our solar system to circle around the center of the galaxy. And so that's a regularity, but if you don't get the parameters right, we'll never do it. For example, right? So and this is, of course, an argument of our opponents to say, oh, if we change the parameters, everything can be seen as regular. But that's not true. So the way to do it is the classical way to look for regularities is that you are saying this is really true. If I cannot formulate the behavior of the system with 5 variables or less, so then when I can, or later on when there were better computers, 10 variables or less, then I can choose, like the Navier-Stokes equation with 5 variables. Then basically, so then I cannot have a partial differential equation. Without a partial differential equation, I cannot have a law of nature. All laws of nature are either ordinary or partial differential equations. That was the old definition before we had AI. And so from this you can see that I give a lot of importance to AI. So before we had AI, we said, okay,
And why so few variables? Because if you have too many variables, so there are only very few partial differential equations or ordinary differential equations that you can solve analytically, where you can find the solution, which is always an equation, right? If you need an equation as a solution to a differential equation. And analytical solution means that you can actually derive this yourself, and then you can plug the equation into the partial differential equation, you make the derivative, and you see that the two sides of the equation match. Then you have the solution to partial differential equation or differential equation. And this was the criterion for a long time. Physicists, when they were discussing in the 1950s, said, no, you cannot set up a partial differential equation for this, forget it. But like for turbulence, so Kolmogorov, one of the greatest geniuses of mathematics of the 20th century, he tried to make a system of differential equations for turbulence, which is actually discussed in the appendix of our book. But when you read the appendix, you can see he failed, and he even saw it himself. That's when Heisenberg said they will always fail, because the problem is too hard. And so now the criterion, you could now say that the new criterion with AI is because now you can have systems with billions of parameters, of variables, right? So you can have a variable space of 2 exponent 12. This is the input vector length of ChatGPT, and then you can have in the equation billions of parameters. So these equations are built like this. And now I make a very, very simple form, but usually you will learn more. They are made like this, so you have basically. So this is an estimator of what the model is supposed to calculate. For example, span, yes, no in the span field. Now you have something like this. So you see here, I'm using I'm only using 2 input variables, x1, x2, but because I have now many parameters, and I can now make polynomial variants of the input parameters and arrange them with different parameters. I can get many more parameters than I have input variants of the equation. And if I now make such the deep learning models are such equations. They have of course thousands of input variables and billions of trillions of such parameters. And so they are basically such equations, which are very, very long. Once in 2013, when in the industry, the head of IT, these people who are responsible for the safety of the algorithms that they are running on their computers were not used to this, I had such a model with 6,000 parameters. And I think 128 input variables. At the time, it was already a decent model, right? Now it's small, but at the time it was, and he wanted me to print the model out to stamp it approval. So he said, no, you have to print in Allianz, we are printing out the models, reviewing them, and then putting a stamp on. And actually, it was funny because then I printed out the 6,000, this whole equation. Nobody has ever asked me before, so it's kind of hard. So you need to figure out how you can, because it's not stored like this in the computer. So you need to figure out how to print out. I managed, it took me a day or so to write. I had to write some software that created this type of output that I printed out for him. And with all the values of these variables also. So not only the form of the equation, but after the equation also the variables. And then he said, why are you, so he looked at it, and then he said, but why have you printed, he was himself a mathematician, right? So not incompetent. Then why have you printed out the value of these parameters behind the and said, oh, because they will change every week. What? They change every week? I cannot approve this. I said they have to change every week because the data changes. When we train the model, these parameters will change. That's the whole purpose of the model. What? And I said, and actually, even those terms will change. The linear combination of the input. What? He said, I cannot approve this. I cannot approve this. And then I said, but I have already come to you. You are the CIO of the Allianz. You're supposed to be the boss. You are missing out on the new age of AI. So what do we do? I said, I'll teach it to you. And he said, but that's impossible. My calendar is too full. And I said, well, let's meet in the evening. And he said, I said, you cancel some of the dinners and you just learn it. I teach it. Then I taught it to him. And we met him 3 times, and then he understood regression. I mean, he was a mathematician. And then he stamped it. And then what he still requested is that every month the whole model should be printed out again with a diff. So with the print out of the differences to the previous model. So why am I telling you this? I didn't know how to got to the story. Well, to explain to you that now we have this mathematics that we can automatically generate such models. And these models, in the end, what they do, they describe a relationship between these input data and the desired output, which can be spanned as no, but which can also be the next syllab in the GPT output, right? And so, well, this is on a slide, but the point is that now, what are now the parameters that define regularity? So this is very important. So I would say, if you have data, this is a slide I don't have, but if you have data over time, right? Now you train a model, and now the model converges. And so this is the error of the model, right? It converges and stays like this over time. So this is a converging model, like a damping pendulum. Here's the error. This is data over time. So if this converges and stays at this in a certain boundary of error, then you know that you have a regularity, that your model is about regularity. But if you add the data and the model goes like this, like my model with the bird flu, right? Where suddenly, when the bird flu happened, the model deviated totally and the error exploded, then you don't have regularity. It's very holistic, right? But why is this holistic? Because this is also a holistic equation. We are not anymore in this nice world of Einstein and Schrödinger, where clever people look at problems and figure out differential equations. We are now in an age where we give data to a model, have a certain algorithm that is able to parameterize all of this and calculate also these interaction terms, by the way, and parameterize all of this, and then we just look at how the error evolves, right? And this is also what happens with the Google spam filter. If there's a genius who invents a totally new spamming idea that makes the spam filter fail, it will also go up, right? Or so that's because the people who invent the spam are complex systems that have new element types and irregularities, then the system will fail. But so basically what we have, if we look from this perspective at ChatGPT, ChatGPT is now in a stage where any new data from the internet will not affect its error anymore. That's what Barry showed yesterday. Now you understand a bit more mathematically why ChatGPT cannot be improved, because the regularities which are present in the language data on the internet have been used up. And what's actually going to happen to ChatGPT, for reasons I will talk to a bit later, is that it will go up again. And that has to do with entropyification, but not in the sense that Barry said it yesterday. Okay. Now I think I have said what is here already. So I will skip this because, I mean, how much time do we have? Till 1?
No, 12:15.
That's terrible. so I have too much material.
Let me check, but I think that's the
Yeah, take your time to check. I will continue. So I've already said to you that the changing phase space cannot be modeled. I've given you the water bottle example and the wave example. This is something I haven't talked about, the process trace.
Sorry, yes, it's 12:15, 12:7.
Yeah, that's all. But that we can still bring across the most important material. So the next modeling, so process trace. So if you have a complex system, so this is a trace of a process shown here, right? So it's basically the situation of a particle in a 2-coordinate system over time. And if you have a non-ergodic process, then you don't get a regular trace. And the samples drawn from such a complex trace are never representative of the process behavior due to the non-ergodic character of the process. So there is no regularity in the process, then you cannot have any model of the phase space. Now, here is a slide that summarizes what AI is in one slide. I use this kind of beer where you place your beer. So how is it called actually in English? I don't know. Anyone knows? Beer coaster, it's called. So it's where you put the glass onto. So basically, this is very German. So when you go to mathematics course in the algebra, the professor explains what a Hilbert space is. He says, things like, I have an explanation of the Hilbert space that fits onto a beer coaster. And this is a German way of saying I simplify it now. And he actually explained, Aldi, the shop where you can buy groceries, Eldai, this chain. So he expanded the Hilbert space, but it was Eldai. It was a shell, the relation of it was quite funny. So AI is applied mathematics for the identification or mapping of recurring patterns into machines. It's not a model of the human mind or even of animal intelligence. So AI does not think or intend. Now there are two types. So this is the general definition of AI, what AI really is. It's just applied mathematics that can find regular patterns automatically, which is wonderful. And then there are two types of AI. There's deterministic AI, like IBM D2 chess computer from 1996 or 97, which has rules, search trees, logic, that's explainable and reliable. And this type of AI is, for example, built into the whole defense industry. There is also stochastic AI that you've done a lot of calculating the trajectory of incoming missiles is completely using this. And then there's stochastic AI, which is, and those rules can also be partial differential equations, of course, right? Any type of rule. And then there's stochastic AI, which is regression, classification, pattern recognition, which is not explainable and probabilistic. And examples of this are AlphaGo and ChatGPT, the so-called neural networks. And what I've been doing all my life is creating hybrid models. So I've recognized very early on in 1999, I saw it for, I was 28 and I had dealt with AI since half a year. And then I recognized that there are these two types of models. And then I thought, what is the best? And then I figured out how to combine them. This is how engineers think, right? Engineers see that their technology is available and now they combine them to achieve a goal. And this is what you should do. And also ChatGPT actually is full of deterministic software. It's of course, if you look at the whole software, I don't know the source code, but I can tell that there are many deterministic elements of it. For example, the fact that it never gives the same answer to the same question. That's a cheap trick. They do this by slightly scrambling the input. so that's the output looks a bit different every time. And because if they would use the bare model, it would always give the same answer to the same question. Question? You're puzzled.
Well, no, but no, that's what I wanted to. Maybe also the analysis of instrument. I thought I saw ChatGPT also using something like Python or something that you compute numbers, and that will be the truth.
Yeah. So the software that is, of course, well, I mean,
I didn't know how to.
Yeah. I see what you mean. So everything running on a Turing machine is ultimately deterministic because it's based to the Turing church thesis that only certain combination of computational steps are possible. However, why we call this equation a stochastic equation is that it always needs to be formulated correctly by at the end adding an error term or several error terms. The error term describes the stochastic element which leads to the fact that why this is also only epsilon hat. So if you have a true functional, it looks like this. Like, for example, this functional, right? That's f of x equals 2 plus x. So you insert 3, you get 5, you insert 7, you get 9, and so on. It's a linear function. It's totally deterministic. It has no error term. But in stochastics, you have y hat equals f of x minus y. So here you see you have an error that there's a difference between the true function, the function, and the true outcome. So this is a true outcome. In a regular, totally perfect, non-deterministic equation, it's different to 0. But in stochastic models, there's always a difference because the function is not a perfect mapping of reality of the data. And so this is why, even though the computation steps are all deterministic and Turing-like, or Turing-ish, we have this difference is not 0. And because of this, it's called stochastic function and not deterministic function. That's all. But the way it's calculated is of course deterministic, right? And once this function is finished, so once it has been calculated and it's used, it always gives the same result, which shows that once only its making is non-deterministic, but when the function is running in the computer, is deployed, it's deterministic. So that when you have the same input, you should get the same output. That's why Google Translate gives you always the same output, because Google Translate doesn't have to do consumer tricks. right? That the fact that ChatGPT gives out different answers just to make it more sexy for the consumer. But Google Translate, you want to have the same answer for every translation task. So you only get a change of Google Translate when these model parameters get updated. But if the model parameters don't get updated, it does the same. So you're right. In the end, all of this is deterministic, but the distinction between stochastic and deterministic comes only from the way they are calculated. Okay. Now comes a very important thing. So how does stochastic AI work? So basically, you always have an input and an output, and the AI is just the relation between the two. So for example, you have an email text and the output is spam, yes, no. Because many users have clicked on the spam button, and this is recorded. And now we have for every text, billions and billions of text, we have a decision whether it is spam or not. Of course, users don't click all the time, but we have many, many examples. And now you can, in so-called supervised learning, train a mathematical relation that mimics the decision of the human whether it's spam or not. Right? And of course, people misclick, so they click something spam which is not spam, or they actually don't recognize that as spam in that spam. So they really believe that they can get a bigger penis, right? and yeah, and then or bigger breasts or whatever, that's possible. Anyway. But or get rich overnight and so on. And so they fail. But in the end, most humans are good at detecting the spam because they have a certain intention of using email system, right? And the intention is not that they should buy fraudulent stuff. And so they make this decision, and now you can mimic this decision as a simple system. So of course, the system that makes the decision is complex, but AI mimics this. It maps the complex system into a simple system, right? So we have a complex system making a real decision, but that's mapped by a function into a simple system. And now you have a simple system, which is just such an equation which can mimic the human decision if this relationship does not change. Now, if a new spammer is in town, who has found a new way of making elegant spam, who is not recognizable as spam immediately, then the system will break. So it's always lagging behind reality because it's trained. This is the difference between human intelligence. So I can very often see there are new, we have a department in my company that is tasked with preventing people from clicking on fraudulent emails, and they themselves invent pseudo-fraudulent emails. And now they had a recording actually in one event in an email of our CEO which was made using AI, where he said that wire transfer money to the bank account. And the bank account was the company's own bank account. So if you obeyed it, it didn't matter, but actually 2 employees who did it. They transferred money to his bank account. Because they said, it looked like it was his email address almost, it was just one letter change, and then you could click on the link, and he was talking and explaining very important. There was a new program to allow the employees to become co-investors in the company, acquire millions of a share of the company by investing €100. And so some 2 employees really wire transferred €100 to his bank account. It was kind of depressing. And I guess through the 2 where I was right. But so that's when the relationship changes. But if it doesn't change, you can estimate this function. So this is fundamentally how all AI systems work. Now, of course, it's not so simple with ChatGPT, but it's always this fundamental idea of having an input and an output pattern, and the mathematics of AI is just the relation between the two. I have so much material, I have to skip this. Yes, I go to this. So, because I still have one, or I want to bring you more the interesting stuff. The rest is important, but you can read it in the book. So here you have again, so supervised learning is a relation between input and an output. It's computed, the input data are also called independent variables, the output data are called dependent variables or outcome. This is very classical. This is what Gauss and Legendre already invented, and there was another guy who I always forget, of Eastern European, also involved in this. In the book, I even managed to actually get the spelling of the French Z letters right in the name Bostich or something like this. And they already saw that you can using data calculate such functions. So I give you a simple example. So here you have a correlation between the height, body height, how tall you are, and body weight. And this relation looks like this. If you not measure individuals, right? There are of course slim, tall people and small people who are very fat. But in the end, you have such distribution now. You can Legendre and Gauss discovered that you can draw a line, that you can minimize the distance. This line is f of x. The dots are y. The real outcome is, you can say, if I have f of x minus y, I can measure this difference here, right? All these differences, and square them, and this is the sum of squares. And then I can make the least sum of square. Then I can basically take this and say I set this to 0 and make a derivative. Oh, it's full derivative. Make a derivative of this. Then I find the minimum of this, and this gives me this function. Right? So I can parameterize this function by using the data. And this recipe, because when I minimize this function, I minimize the errors, so I get a function that's as close as possible to all the dots. This is a fundamental trick that they invented 220 years ago, by which all the AI models are made. The big difference is now that you not have not only one variable, but many variables, and that the equation, that resulting equation has not only this equation has a form f of x equals beta 0 plus beta 1 times x. So it's a variable in one equation with two parameters. The first is this one, which is here the intercept. It's here -1, for example. And the slope, let's say, this is -1, this is 1, and this is 2. Then the slope is maybe beta 0 here is approximately -1, and beta 1 is approximately 2/3. Right? So we have a slope function with two parameters and one variable, and you can get beta 0, beta 1 by solving this equation. And then you can, for linear equations with many variables, you can still very easily solve it and set it up. And if you want to know how this works, you can read Trevor Hastie's Principles of Statistical Learning, which is cited many times in our book, which is the classic, and which is what, who of you are AI students?
Yeah.
Have you had Hastie?
Elements of statistical learning.
Yes, sorry, elements. Yes. Elements of statistical learning. And then basically you learn all of this, and it works really well. Now, if you do this, you can also do this. Now, if you do this for more than one variable, you then get what is called a hyperplane. So now you have 3 dimensions, right? And now you split the data points not by a line, but putting a plane into this. And this plane will then somehow split the data point in 3D. And as you increase the dimension, you always increase the dimension of the specifying line. And it's called a hyperplane. If you are in more than 3 dimensions, it's a hyperplane. But this hyperplane will then, and then if you allow for combinations of the variables, and then you get a shape that can have basically be formed irregularly. I mean, it's still manifold in the mathematical sense, but it can then be shaped. It's not then a plane anymore, but it can be shaped. It's like hammering against it. And the data will decide how much you hammer against it to change the shape, and then you get an irregular shape. Oh no, it's a regular shape, but it's still a kind of, it's everywhere differentiable and continuous, the shape, but it's a manifold in the sense of 19th century mathematics, but it's what's his name? Invented this Riemann. It's a Riemannian manifold, but it still is mathematically well defined. And now you're doing partial derivatives. So so now you have derivative. Now we have not dx, but we have dx1, x2. Now you do partial derivatives by all the different variables. This way you can now find a local minimum that also minimizes this error term with regard to high-dimensional data. So it is still the same principle, and it stays like this even for the most complicated AI tasks. It's always a shape that somehow explains the relationship of the function to the data, but it can get very complicated. But it's always obtained by calculating derivatives. And it's called gradient descent, neural networks, and there's a book by Benjo called, you know, the Benjo's book about neural networks. Deep learning, yes. And there it's explained really well how it works. And if you read the book systematically, and sometimes he gives literature for those who are outside the field, you have to then read another book before. But you can really understand how it works. And it's always this core principle. It's a minimization of a deviation of a function from the real outcome. And you can, by doing this, you can get a function, but you can also get an operator. So a function maps an element of a high-dimensional space, like a sentence, to its span or not. This is then R. It's a one-dimensional space. But you can also map a high-dimensional space to one other high-dimensional space, which is called an operator. And Google Translate, and also, of course, the other sequential models, ChatGPT, they are operators because they create as output high-dimensional output. Right. And here you see again, this is a loss function. You see it's y minus f of x squared. That's the most simple one. But there are other loss functions that are more complicated. And now, what you see here is now the types of models that we have today. So this is now about the next step, which are the deep neural networks. And it's a bit simplifying, or very simplifying, but doesn't matter. So in principle, deep neural network is a way of architecturally designing the future algorithm that will work to calculate the function I just described. And it works, it uses input variables, then you have a hidden layer, and then you have the output variables. And what it does, here you see your input variables. So here it was just one dimension x, but you can have more. Here you have, I think, m variables that are input variables, and then you have weights. Now the input variables get multiplied with the weights, and it's summed up, and then there's an activation function which decides whether the linear combination of the variables that was created by this step is propagated further in the neural network. That's basically how it works. And then you get this, you can have this here, the middle part you can have many times. And then you have this, that's why it's called deep learning, you have many such layers. And if you think of these many layers, they give you a lot of parameters, because you have different parameters, W at each layer. And the way that they can combine them in a different way, you can have different activation functions. So activation function essentially, very classic was the hidden function, which says if the input variable combination is like this. So basically, until here, everything is set to 0, and then it obtains a linear value. And there are many other activation functions, arcus tangens and others, and tangens, and all of them contain different rules how you can basically deal with the combination of the input variables. But it creates in the end different shapes of this equation. It just changes the way the variables get combined and the parameter gets multiplied with the variables. But that's what it's doing. And engineers who engineer neural networks have spent the last 15 years trying out different ways of combining the variables, different ways of making the thresholds, activating, and Jürgen Schmidt was a pioneer. He's famous because he was one of those who has a very elegant way of designing. So he had designed also that the resulting activation should go back into the input, that's a recurrent neural network, that it could also determine the threshold that is used. And this way he made the adaptability of the input variables. So what he basically achieved, and all he wants to work with his principle, is to make the parameterization of these variables, the parameters, much more flexible. So by introducing all these loops and steps of influencing this, he achieved a much more fine-grained way of adjustable parameters. And it sounds trivial, but it was a superb insight and extremely clever and admirable. And that's why he and not this idiot Hinton should get the Nobel Prize. But you know, the Nobel Prize, when I was in my 20s, I thought the Nobel Prize was like a great thing. I mean, I already saw that the Nobel Prize for literature was bullshit, but I still believed in the Nobel Prize for the other sciences. But now I don't believe it anymore. I mean, it happens that sometimes the right person gets a Nobel Prize, but very often it's not the case. And it's like one very good example is Einstein, who got the Nobel Prize for the general theory of relativity very late, and because when he published his special theory, people thought he was mad. It took a very long time for him to be accepted. That's one example, but there are many more examples. One other one is Hans Krebs, who found the Krebs cycle, which is a fundamental cycle for energy production in our cells, and he got a letter from nature saying that they rejected his contribution, which was, I mean, he's a, people like him occur once, there are just a few in 100 years who are like him, you know, total genius. The letter was, we regret to inform you that your contribution is not of sufficient interest for the general reader. It got rejected. Came from a rejection that later he had it on his wall in his lab. He had this letter from nature on his wall to show how absurd the system is. Anyhow, so this is how they work. Now there are, what is very important is a long time neural networks were only doing supervised learning, so that you had always to train them, to parameterize them. You had always input and output data. So basically, you have this form, n input vectors with n output points, and the x is p-dimensional. So the example I gave you was the hospital bill classification engine was 128 dimensional. I think now ChatGPT is, I don't know, 2048 or 4096 or 8192, some potency of 2 because the binary vector. I don't know what the current size is. That's the p-dimensionality, and now you get an n times p data matrix. So that means that you have, I showed you this matrix before, that you have basically, what is this? Doesn't matter. You can draw it again. So it's basically a matrix like this. We have p variables here and n variables here. These are the observations, like sentences to train a neural network, for example, or emails to train the stem filter. And here you have the variables. And now you also have, usually in unsupervised learning, you don't have an outcome. In supervised learning, you have an outcome, like spam yes or no. But unsupervised learning, you don't have an outcome. And they then create the outcome by taking the sentence and, for example, deleting from the sentence a word. It's called skipgram. So basically, then this algorithm is trained to impute from the missing input the complete sentence. So they also use an outcome, but not a separate outcome, but a purely syntactical outcome. And this is then used to let the system learn, or let the system be parameterized to identify from the context of the sentence. So, for example, we get a Christmas tree for Christmas, you remove tree, and then the machine is supposed to reconstitute the sentence and insert tree again. You can do this also on the level of letters, removing letters from words and so on. This way, if you run this neural network and ask it to minimize the error, so if here this is the word that should be put back if it says tree, but if it doesn't give it without tree but something else, there's a way to calculate this difference. Of course, it's not as simple as that, because difference between letter sequences have to be formulated in a more complex way. But the error is calculated, and then the error is minimized. And if you do this with a lot of sentences, you get a model. This is the key how LLMs work, that is parameterized to reflect the structure of language. This really works. This is, when I saw this for the first time, I could really not believe it. This was in 2013. I first, like, I was waiting as a stupid physicist who wanted to reject Einstein. I said, no, that's not the case, it's wrong. And then the colleague says, Jobst, aren't you the one always telling the story about Einstein? Then I got totally red in my face and was ashamed. I spent the night studying it. And the next day I said, okay, it will work, it's great. So I recognized it. And then I was looking for ways to use it myself. And this is very different story. So it's very hard to use these models in economic context. And we will get to this soon. But this is how it works. When you hear of unsupervised DNN or so-called foundational DNN, they are made like this. And then the procedure is always the identification of local loss minima using gradient descent or model loss function. And then you get implicit, and here you have billions of variables. Okay, and so this is how it works. Now, this is another slide that explains that this is very important. I won't go into the details, but what this slide and what we also explain in the book is that these models need a lot of data. So they need so many data that they'll suffer. That the reason that they need so many data is basically shown here, that the sample density in the data space shrinks exponentially with the number of variables you're adding. So the more variables we are adding to this vector, exponentially more data points. And so then you can very quickly get to a state where actually the entire text corpus of the internet is small. And this is what the slide shows you. And this is why ChatGPT isn't improving anymore, because of the data grid of the models. So, so for example, if you have 10 variables and 500 data points, that means that the density of this is a p-dimensional ball with n uniformly distributed data points. So imagine a ball of p dimensions with a number of data points given as n. And now the median distance from the ball centered to the closest data point is given by this equation. So with just 10 dimensions and 500 data points, the median distance is 0.52. So that means that even there, most data points are closer to the boundary than to the center. So that means that if you add more dimensions, at some point, all the data points will be at the border of the ball. This is what this equation shows. This is a topological law. So you cannot circumvent it. So that means that if you have now 100 dimensions, 500 data points, all of them will be at the very periphery. And so now what these algorithms do, as I've shown, they try to put a line in the dense area of the points. But if you imagine that all the data, this is interesting for you, isn't it? But if you read this. Yes, it's a constant dimensionality. So if you now you have to put a hyperplane into these points, but now all the points are gone. They're all they're not anymore available. And this is what happens with the curse of dimensionality. And or data greed. And now to finish this section on stochastic models, I've alluded to this already yesterday, but it's impressive to see the pictures. Let me try to get rid of the sun. God. Oscuramento. I know Latin, so I can at least passively. and Spanish and French, so that helps. But I never learned properly Italian, unfortunately. So it's the best of those languages. No, it is, because it's a more efficient way of Latin. It's an improved Latin. So these are the pictures I wanted to show you. Well, this is enough. So this was Google Gemini. I think the version, was it 1.5 years ago? Yes, it was released 1.5 years ago, I think, in fall of 2023. And so when you ask it to produce a picture, there's an AI that can produce a picture based on a text input. And when you ask for popes, it gave only women or black popes. But neither has ever existed, right, in the history. I mean, I think that we might have a black pope soon, but if I look at how Christianity is evolving, you know, that it's basically fading in Europe and in the Northern Hemisphere, that might happen in the future, but it hasn't happened yet. But Washington definitely was not black, and of course, the United States, Germany, sorry, would never have accepted a black person as a soldier of the Waffen-SS. So why does the model make these mistakes? It had to do with the training material, because you know the training material resides from the relationship of this matrix of data to the training vector, right? And if you met y, which is the outcome, and if you what they did at Google, because they were so politically correct or woke, as I said, they made this relationship so that the model got punished for showing white people, and also got punished for showing males. It should show females or non-white people. It was optimized for this, and because they trained it like this, it was not possible to correct the model. So when they gave the model counterexamples of this, the model didn't react because it was so skewed to this relationship, so it couldn't be corrected. So that means that the optimization is a problem-specific loss function that's not generalizable. So you optimize the function to a certain relation between this and this set, or where's this two sets? And like you get for this one set and this other set, right? So so the points here are basically describe the relation of the two sets of input and output data. This is the function. So this the function, as you can see from the simple picture, totally depends on the choice of these two sets, right? And so if you put here a woke set of outcomes, you get a woke function. You can't change it. Then there's a close dependence on the selected training sample and its specific annotation. So it depends very much on what you do here when you assemble the data and what function you will get. There's a big problem if you have for one data point, like here you have one data point with two outcomes. But if you imagine that now a function should be determined, should go through this or this point, the function will go through the middle of the points. Or depending on how it's specified, maybe different, but it cannot go through both points at a time because this is not a mathematical function. This because mathematical function always has to give to one x value, one y value, not several values. Otherwise, it's not defined. Otherwise, it's a relation, but it's not bijective. And these functions are all bijective, right? And so because it has to be bijective, it can't do that, and that's called actually singularity, by the way. When you have such a, so for example, the function f of x equals 1 divided by x has this shape. And here, it's get almost vertical, so here it's not defined. So that's singularity. Because in the infinity, close to 0, at minus and plus infinity, it would assign the same value to several data points. So it's not defined. And so when humans do this, humans give different annotations to the same input. I mean, it's when we look at, when males look at women, they will never agree, very rarely agree on whether they find the woman attractive or not. Many people don't think Marilyn Monroe is attractive, for example. And it's a good right. I mean, and they prefer maybe more slim women and vice versa. So humans tend very much because of their different intentions, they tend to appropriate different outcome values. This is very hard for the models. Also, the models fail when the populated sample space is sparse. So then I showed the curve of dimensionality, when there are not enough examples, there's no way to put the hyperplane into the space. But real intelligence is actually the ability to just do that. You are now confronted with something totally new, where we have no examples, and you find a solution. And this is the core of real intelligence. Models cannot do that at all. And this is something, I mean, when I point this out to the AI believers, they always say, yes, but they will. This is a statement of fact, right? It's not a statement of mathematical truth. There's no guarantee that the result will be corrected as soon as an error is detected, so it was not possible to correct this. The algorithm understands nothing, it cannot predict its own failure, so this is a failure, total failure, right? But the algorithm cannot detect this. I mean, if you put in sect leader, the upper pictures would be correct, right? And but in fictional alternative history, the lower pictures would be correct, but they are not. The algorithm cannot model far-reaching relationships, so that's very important. So all these models, so if you look at the core model of GPT, it's a transformer architecture with a limited semantic scope. So the relations that can be parameterized are very narrow. So if you give it a Dostoevsky book, it cannot adequately summarize the whole book. The summary, so you could, I don't know whether I'm not, unlike Barry, I've never spent any time playing with these models because I've mathematically looked at them and see their limitations. I always said to Barry, don't waste your time. But what Barry did was that he came up with fantastic dialogues that he's using. Unfortunately, yesterday he didn't show the dialogues, but some of them are so funny that you have to laugh out loud. How he makes the ones say nonsense. It's quite amazing. But if you would ask me to summarize The Idiot by Dostoevsky, I'd give it, I don't know, 3 pages to get some. A human being would describe as a crime novel with a court case and the main characters and who cheats on whom and so on. But I think, because the problem is that this you can only realize as a human reader, but the novel is one of the most complicated novels I know. It deviates so often from the main story, and there's so many side ideas. It's totally, some of it are sometimes 20 pages of pure philosophy, like the dialogue of the great inquisitor with Jesus. When Jesus comes back to Earth, I don't know if you ever read this dialogue. It's actually worth it. It's one of the best pieces of literature ever written. It's not in The Idiot, it's the Brothers Karamazov. Sorry, I was totally wrong. So all I've been saying was about the Brothers Karamazov, not The Idiot. So the Brothers Karamazov are a court case story, and they contain the great inquisitor. And I think to summarize this correctly, you need to understand the relationships, the long distance relationships in this novel. I don't think AI can do that because of the way the models are trained. It cannot model the semantics of mental categories. So it cannot, like we can say this is a container, for example. It's not only bottle, but also container. It can't do this. So it cannot interpret any images or language. It can only summarize language. It can also find the next most likely token, but it cannot say, for example, it cannot even say this is racism. So my son tried, he put into the Google has a tool for detecting so-called hate speech. So he put in, I'm a fat, and he really used the N-word. I'm a fat N-word woman, and so on, and it was classified as hate speech. But then he put in an extract of the speech, but if you say, I am a fat idiot, or about yourself, you don't even have to use N-word, it's not hate speech, because you can incite yourself as much as you want. Right? There's not, I mean, as long as you're not involving anyone else, it's not hateful to incite yourself. It's your good right. You know, if I would have missed today's course because I was sleep too long, I would curse myself that I'm an idiot and I failed. It would actually be true, so I can do this. But it was classified as hate speech. But when he inserted the part of the Goebbels speech, that Goebbels gave at the in 1944, the famous speech where he said, "Do you want total war?" You know, this is basically one of the most sublime and concentrated forms of hate speech that ever was done and given by anyone. If you put this into the model, it says it's okay. It gives a green light, says it's okay. So it obviously cannot understand anything. So they don't they cannot interpret languages. This is very important. So the models are very impressive in how they deal with language. They can translate language roughly. They can write summaries. They can give answers to questions, but they don't understand what they're doing. Therefore, when you ask for interpretation, they fail. They have insufficient accuracy for critical situations, like driving a car. And when you increase and manipulate the training procedure, then that then leads to false generalization. So they have many problems, these models. And I think I have now a section. So I've prepared far too much material, unfortunately, but I will save some of it for April and skip it. So this is about reproducibility of AI, which is depressing because it's not reproducible. But most of it is not reproduced, but I will skip this now. And I will now give you 10 minutes about how I see enshittification of the internet. So what is happening at the moment is that a lot of the internet content is itself generated from large language models. So because people are generating text using large language models, which are then posted on the internet. And I know also of hackers who actually create HTML pages with white text, with passage of white text printed on white letters printed on white background. So that the human being cannot see when he renders the HTML page with the browser, cannot see and so it's a normal page which looks like a normal, you know, our club is meeting next Thursday to play poker, but then there are thousands of symbols which contain crap that are put there to sabotage the LLMs. And so this is done systematically by people, but nobody finds these pages because it's hidden just with a very simple trick, white font and white background. Others do just post, users just create LLM content. Even I think on Twitter or on these platforms, I don't use them very much, but you can also, there are now functions to enhance your content with LLM. So you can draft something and click on enhance content, then the LLM will rephrase the content and post this. That of course also, that means that more and more content that gets posted on the internet is now affected by LLM output. And so this is what people call LLM autophagy. So it was first detected in 2023. So the so-called generative model is a stochastic sequence generative model that produces an output sequence that is most likely given input sequence. So for example, here you have, this is your output sequence, this is your input sequence. And the model just calculates which output sequence given this input sequence is the most probable and puts outputs. That's all they do. They're just probabilistic machines. And now, if you have data, so you have now data, and now you are doing sampling. You're sampling from the data. And of course, if you have a finite sampling, and all samplings are finite, then probable events are overestimated and probable events are underestimated, because you know this very well. So let's take a typical distribution of how internet data look. So for the phenomena, the internet are distributed like this. So the gamma distribution. And if you sample randomly from this distribution, you get, of course, more events from it. The more frequent events are then seen more often by the model. Now there's a model fitting done, and this fitting is done to this part of the distribution. So the rare events are not sampled. And so the probable events, now this tail shrinks. It gets shorter and shorter because if the model output is put back into the data, the rare events are diluted. And so the model see less and less of the rare data. And this is actually the opposite of what humans do. Even animals, so animals have a built-in capability of actually being attentive to rare events. So this you can see when you walk on a street and there's an irregularity, like for example, a car has stopped on the street, but it's oriented horizontally to the street. You immediately see this, right? What's going on there? Why is the car standing on the street 90 degrees turned to the traffic, right? And the other cars would stop, there would be chaos immediately, right? And so human beings are very good at spotting these irregularities. And so they are, especially human intelligence is dealing with this. It's the ability to deal with this tail. Also animal intelligence, but the machines get less and less good if they don't see this tail. So this is very important. Then what happens next? So now you have real data and you have the state zero. You make a model. Now you sample from this model, you make the next model, the next model, the next model. And every time you insert, you're diluting your data because you are reinserting LLM-generated text into the model. And so the model decreases in quality because you are only concentrating the model on the frequent events. And the frequent events are, of course, boring. So that's why it's boring. Most of the material on Netflix I cannot focus because it's all the movies and series that are given down. Most of them are repetitions of former material because there's very little artistic content. So artistic content can also be Star Wars, the first Star Wars. When it came out in 1976, or 77, I was a boy, I was 6 years old and I was watching it with my dad in the cinema. I can still remember almost all of the movie from how I perceived it at the time. And because it was, I didn't watch many movies, so I was anyhow impressible. But also, even for my father, he remembers it now because it's 50 years ago almost, but it was artistically valuable because there was so much novelty in it. And lack of novelty, humans get bored, right? But the machines don't notice. They just train themselves and become more stupid and more stupid. So here you see what happens in the experiment. This is an original model to create handwritten digits. So the model was trained on real handwritten digits, and now the model should create handwritten digits. Can anyone guess from which country the samples were drawn to create this model? You can see it. If you look at this rectangle, you can see it. It's from the United States because it's 7. They do the 7 like this. In Germany, we do the 7 like this. Anyhow, now you feed the output of the model back into the model and dilute the original data. At the end, it will only create zeros and ones. And that's because zeros and ones dominate the decimal system, as you know. And so, at the end, the models can only do the most, it's here, right? It's here at the thick end of the tail. It can only do zeros and ones. And not even very good, they're kind of blurred. Right? And this is the same with pictures. So when you ask the model to generate a picture, this is artificial face generated by an LLM, but now you are actually inputting the output of the model back into the data. So you're just taking the pictures that were made by the model, putting it into the data. And the more you do this, you can see here these hatched sections of the face. So the face becomes unhuman. And it becomes unhuman because the algorithm, this is basically the emanation of the architectural fingerprint of the model that becomes visible in the pictures. And so basically, the internet is flooded with such synthetic data from generic models. And synthetic data are also used all the time by model engineers. So I was at a conference, at a very important conference, the German Association of Physicists in 2017 or 18, speaking about AI. Before me was the head of the Max Planck Institute of AI, a total idiot. It's interesting, you can become head of the Max Planck Institute and be an idiot. And he said, we don't have for the self-driving car, the movies that we have from the cars and the sensor input is insufficient to cover the rare situations, like hail. Hail is rare as a weather event, so there are very few recordings of hail. Hail is certainly a phenomenon here. Or you are driving a car at night with very heavy fog. Then all the photons get reflected. So you are blinded, right? So if you switch on your headlights, at this night intensity, the blue night intensity, far-reaching headlights, it has green and blue. Green is low intensity, blue is high intensity, you know what I mean? And then you don't see anything anymore, right? And so all these things don't happen very often. Heavy snowfall, icy road, and so he said, oh, we just have to add synthetic data to our training data, then we get better models. And I was speaking after him, I said, you know, if you do that, so what you obtain, you are a Gibbs sampler is a machine to create synthetic data. And basically so it does this. It takes data and creates an outcome. Now, when you train a stochastic model, you just do the following. You just calculate the inverse of the Gibbs sample. So when you basically put only synthetic data in a model and then train the model based on the output of the Gibbs sample, it only creates the reverse function of the Gibbs sample. That's all you do. And the guy was just shocked. You could tell in his eyes, he had no answer anymore. You know, the audience, a third of the audience who got this was laughing out loud, you know. It was kind of interesting to see how the hype is distorting the minds of these people. I mean, you cannot become the director of experiments if you're totally stupid. So it was rather foolishness, right? He was so foolishly in love with this possibility. He said, oh, we have to use synthetic data. And so they do this. And so it can be much easier, faster, and cheaper to synthesize training data rather than source real-world samples. Very often there are no real-world samples, like in the car example, right? It's too rare. Many events are too rare to be sufficiently visible in natural data, hail as weather condition. Most importantly, as deep learning models become increasingly enormous, we are simply running out of real data on which to train them, yet they need huge amounts. That's the curse of imaginarity. Human annotators who provide gold standard annotation for supervised learning tasks are increasingly using generative models to increase their productivity. So the Indians and Pakistani who do the annotations, they use LLMs and output the LLM input into their task. And because they need to make money, they get €2 per hour. And so they're just too underpaid, you know, it's a cruel system. So they will just use the LLMs themselves to generate their own task. It's really true. Users of generative models tend to manually curate their synthetic data. So of course, and this is of course a bias. So what they do is they say, I want this part of the distribution only, for example. Then of course it's another bias. State-of-the-art generative models typically feature controllable parameters, and they can increase data quality at the expense of diversity. So we have parameters, and they are also biasing. And without the sampling bias, autophagy can lead to rapid decline of both quality and diversity, also even without sampling. And with sampling bias, quality can be maintained, but diversity degrades. So you can, of course, bias a sample towards high quality, but then the diversity, then you also shrink, not in terms of quality, but in terms of diversity. And so this problem is even aggravated in LLM refinement training with reinforcement. So the autophagy of the model is a serious problem. And it has to do with the fact that we can only model regularities, we can only sample regularities, because you have to remember, this is very important, this cartoon, right? That finite sampling always leads to an underestimation of important events, but everything that makes life interesting is rare. Like why is gold more expensive than iron? Because it's rarer in the crust of the earth. Why are very beautiful women able to marry rich men? Right? Or why was I able to get a really good looking woman and nice looking children? Because of my intellect. It's really true. I'm not boasting, it's just true. You know, it's so when you have a rare skill, you get somehow rewarded. And so the machine can only work with a probable event. And so this is a big problem. And autophagy occurs because of the big data read of the model in combination with the finite samples that are available. And this is a very, very big problem. And it basically will end the current AI euphoria wave. Because now think of it, so there is important, just as a side remark before I do this, there's an important part of today's lecture that I will give on tomorrow, which is this, how LLMs are trained. How this is something you should learn, because you will see then a lot why they are limited. So this I will do tomorrow before doing transhumanism. But now to go back, so think of OpenAI. OpenAI is an LLM company that was pumped up with tens of billions of dollars. And now you have to remember that investors want at least they want 20 to 50 times value increment of their investment. So if you invest, Warren Buffett doesn't want this. He wants to buy a coal mine and then get 3% interest rate per year. But the venture capitalists to invest into these fast-growing hype areas, they want 10 times, 20 times, 30 times the investment. So this company has to make trillions of revenue to get the profit that justifies this investment. And if it doesn't, at some point it will fail because investors will stop investing, it will go bankrupt. And this happened now. Why will this happen? Because I mean, what usually then happens is if there's still some usable technology in the company, some of the shareholders will buy it to use the technology. But that's also write-off of the value because basically then what is happening is that if this amount has been invested, right, and this was the expectation, like 20 times, the buying price of a strategic investor is usually like this. So it's even under the total investment, right? So there a write-off is happening, or if nobody is buying it, it's just going bust and the money is just being deleted. And the question is, why is this happening now? The problem with these LLMs is they have a lot of problems. And the biggest problem is that they hallucinate, that they create output that is not factual. And while for entertainment purposes, that's not such a problem, even in a computer game. If the LLM, if you use a chatbot LLM, and the LLM will give the player a false hint, players will get annoyed and stop buying the game. Right? So even if a purely fictive content, reliability and trust are fundamental to human interactions. And if the model is not reliable and trustworthy, even in a corrupted society, if you are in Kenya and you want to get a passport renewal, you give your old passport to the official, you put $200 inside the passport, and you know that with this sum you are certain that you will get the new passport. So even this corruption is deterministic. In India, somebody told me when I was traveling in India how I have to bribe everybody. I had a pile of cash, I put it in all my documents between them, I got through like perfectly, right? But without it, it's very hard. You're getting frisked, you're getting taken out of the queue, and you're getting kind of hints that you should give some money, you know, it's terrible. And so I'm not criticizing India, I'm just saying that it's part of the culture. And so reliability is even necessary in corrupted countries. And so, or in other words, the corruption in countries that are not openly corrupted is on a different level. That's also there, I can tell you. And so it's just not so visible and not so much visible in the everyday life. And so the problem is that because models are not reliable and they cannot be made reliable, you will learn why tomorrow, their price expectations are exaggerated. And so once it becomes clear that with the available data, the model cannot be improved, which has to do, this comes from the non-egoicity. The long tail of the gamma distribution comes from the non-egoic nature of human interactions. And because of this, and this is the key thing that they fail to see, they fail to take into account because of the narrow Cartesian view of the universe, which is only focused on the regularity. Right? Because of this, they have failed, and this will materialize at some point, and then this bubble will burst. And it will be very bitter sobering because there will be no alcohol available to drink in the next morning. You know, and now they're still drinking alcohol the next morning. Quite a lot of it. And that's where Jeffrey Hinton is coming from. He's in this alcoholics bubble. I mean, he's not an alcoholic, but I mean, in a metaphorical sense, of this illusion. And they didn't think of this, you know. And I've been thinking of this very early on, you know why? Because I started with AI in biology. I wanted to model biological systems. I always bitterly failed. And then I said, how can all these textbooks, so I had the first edition of Facebook. And I tried to take the methods and bring them to biology, and then I failed. And first I said, oh, that's because I didn't study mathematics, so I got a mathematics degree, you know. Tried my very best. I'm a Lutheran, you know, always try your best. But I still failed. And then I recognized that nothing to do with my skills, nothing to do with the algorithm, everything to do with the data, because the data are irregular. And so this is a key message for you for today. And before we end the session, any more questions? Yes, please.
Just the data that you cited before, the one that presented the situation and then simplified it. To non-scientifically something.
Oh, this is, so there are two books that you should read for this. One is Richard Feynman's Lectures on Physics. You can find them online. So if you type in Richard Feynman's lectures in physics, Caltech, all of them are at the Caltech. They're available online. It's beautifully formatted. It's a bit like the late 1990s formatting, but it's very accessible. Yeah, you can switch the chapters very easily. You can start, if you know something about physics, you can start in the second volume, chapter 9, where it describes how a tempest works. But if you don't know anything, you can just start at the beginning. It's full of it. It's full of examples of the simplification. Or you can read, you can get, if you want to jump into the philosophical, you can read Nancy Cartwright's book, Why the Laws of Physics Lie, or How the Laws of Physics Lie, by Nancy Cartwright. She is a kind of genius minor. So for me, there are major geniuses like Immanuel Kant who are shaping the thinking for centuries, or Nietzsche is also such a figure. But then there are minor geniuses who are not shaping, but who have incredible insights, and she's one of them. So Nancy Cartwright is such a genius, and so you can then read How the Laws of Physics Lie, which was totally an eye-opener for me. And if you want to get the basic stuff of AI, then you should read Elements of Statistical Learning by Trevor Hastings. The problem is that it is written for graduate mathematicians, right, as you noticed. So it's a bit, if you don't know linear algebra, it's a bit tough. But even without knowing mathematics, at least the first 2 or 3 chapters you can understand or get a picture of how this all works. And basically, if you understand this, then you understand the fundamentals of machine learning as it is done today, and you immediately see its limitations. Any other questions? Good. So it means that either it was boring or not intelligible, or you understood everything. So please also, if you consider again, think about this course, and you can ask the question next time. So tomorrow it's I think 1 o'clock, right? Am I right? Yes, tomorrow it starts at 1 o'clock. Yes. So tomorrow we start at 1 o'clock, and so tomorrow we will do LLMs, so how the large language models are trained and configured, and then we will do transhumanism. And on the transhumanism part, there will be one section dealing with the cultural roots of transhumanism, and then why the goals of the transhumanists like Elon Musk, Yuval Harari, or Bill Gates, why they are about to fail and also fail for good. So this is for tomorrow, and then I will, the stuff I didn't show you from today's lecture, I will basically pick it up again in the end of April when we are back for the second part of the lecture. So thanks a lot, and see you again tomorrow at 1 o'clock.